You exist right now, in this moment, on a world spinning around one star, in a galaxy of hundreds of billions, floating in an ocean of 200 billion other galaxies, scattered across a void so vast that light itself takes billions of years to cross it. And somehow, against odds that should be mathematically impossible, you are here, awake, aware, asking why. That is not poetry, that is accounting. The universe has been doing inventory for 13.8 billion years, and the numbers do not explain you. They do not explain consciousness arising from dust. They do not explain why this particular arrangement of atoms can look up at the night sky and wonder where it came from. And they certainly do not explain why we happen to be alive at the one cosmic moment when the stars are still burning, the galaxies still visible, and the answers still within reach. Because this moment will not last. The universe is not standing still. It is expanding, accelerating, flying apart at speeds that will one day erase every galaxy beyond our own from view. In 100 billion years, any civilization that arises will look up and see nothing but darkness. No distant galaxies, no cosmic microwave background, no evidence that there was ever anything else. They will have no way to know where they came from, or that they are not alone, but we do. We are here in the narrow window of cosmic history when the evidence still exists, when we can trace our origin back to the first fraction of a second, when we can see the shape of creation itself, frozen in light that has been traveling toward us since before Earth existed. This is the story of that view, of 200 billion galaxies, and what they reveal about where we have been, where we are going, and why this fleeting moment matters more than you might think. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. There is a photograph, just one, a single frame captured on Valentine's Day in 1990 by a machine called Voyager 1, a machine that, at the time, was 6 billion kilometers from the place it was built. 6 billion kilometers, that's 40 astronomical units. That's deep into the outer solar system, well past Neptune, heading out into the black. And from that distance, at the request of a scientist named Carl Sagan, who had spent years convincing NASA to turn the camera around one last time, Voyager 1 pointed its lens back toward the sun and took 60 pictures, a family portrait of the solar system. 6 planets visible as faint specks against the void. And one of those specks, barely 1/10 of a pixel wide, hanging in a beam of scattered sunlight, like dust caught in a shaft of light through a window, was Earth. That image is called the pale blue dot, and if you have never seen it, go look, not later, now. Because everything that follows in this video, every galaxy, every billion-year timeline, every incomprehensible distance we are about to discuss, starts there, on that dot, that fraction of a pixel, that mote. Sagan wrote about it in 1994, and his words have been quoted so many times they've almost become cliché. But clichés exist because they hit something true. He said, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Every saint and sinner, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every hero and coward, every creator and destroyer of civilization, every king and peasant, every pair of young lovers, every hopeful child, Every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. That image, more than any equation or telescope observation, is the starting point for understanding scale. Because scale is not just about math, it is about perspective. And perspective is what breaks when you realize that the entire stage on which every human drama has ever unfolded, every war, every empire, every artistic masterpiece, every scientific breakthrough, every moment of kindness or cruelty, all of it happened on a speck so small that from the distance of our own solar system it vanishes into the noise. The Earth is not small by human standards. Walk across a continent and you will feel its size. Sail across an ocean and you will respect its mass. The surface area of this planet is roughly 510 million square kilometers. There are mountains taller than the clouds and trenches in the ocean deeper than the atmosphere is thick. By the measures we use in daily life, Earth is enormous, but those measures break the moment you step outside. From the Moon, Earth is a marble. From Mars, a bright star. From Saturn, where the Cassini spacecraft looked back in 2013, Earth is a pale blue pixel nestled between the rings. And from Voyager's vantage point in 1990, 6 billion kilometers out, it was a dot 1/5 of a pixel across, visible only because the camera happened to catch it in a shaft of sunlight. One more astronomical unit in any direction, and it would have been lost completely, invisible, gone, as if it never existed. The photograph was not easy to get. Voyager 1 had finished its primary mission years earlier. It had flown past Jupiter and Saturn, sent back thousands of images, and by 1990 it was coasting into interstellar space with most of its instruments already shut down to conserve power. The imaging team had moved on. There were no more planets to photograph. Turning the camera back toward the inner solar system was considered a waste of time and resources by many at NASA. The spacecraft was traveling so fast and so far out that pointing its camera at Earth risked aiming it too close to the Sun, which could have damaged the optics. Sagan pushed anyway. He argued that humanity needed to see itself from out there, that we needed the perspective, that it mattered. NASA finally agreed. On February 14, 1990, Voyager 1 rotated its camera platform, captured 60 frames, and then shut the cameras off forever. The data took months to transmit back to Earth. The last of it downloaded on May 1, 1990. When the imaging team assembled the pictures, they found Earth in one of the frames, barely visible, awash in a band of scattered light. That photograph is now in the Library of Congress. In 2001, it was selected as one of the top 10 space science photographs of all time. It has been printed in textbooks, projected in planetariums, referenced in philosophy papers, and cited in environmental policy discussions. It hangs in museums, it appears in documentaries, and yet, for all its fame, it is, astronomically speaking, a close-up. Voyager 1 was still inside our solar system when it took that picture. It had not even reached the heliopause yet, the boundary where the sun's influence fades and interstellar space begins. It would take another 22 years before Voyager crossed that line in August 2012, becoming the first human-made object to leave the solar system entirely. And even now, decades later, traveling at roughly 17 kilometers per second, Voyager 1 is still barely out the door. It would take another 30,000 years at that speed to reach the nearest star. So when we talk about Earth being a pale blue dot, we are not talking about a view from across the galaxy. We are talking about a view from our own front yard. And even from there, we disappear. The Earth is 4.5 billion years old. It formed from the debris left over after the sun ignited, a spinning disk of gas and dust that slowly clumped together under gravity into rocks, then boulders, then planetesimals, then planets. For the first few 100 million years, Earth was a molten hellscape bombarded by asteroids and comets, its surface too hot to hold liquid water. Then it cooled, an atmosphere formed, water condensed, oceans appeared. And in those oceans, somewhere around 3.5 to 4 billion years ago, chemistry became biology. We do not know how. That transition from complex molecules to self-replicating life is one of the great unsolved problems in science. We know it happened. We know it happened relatively quickly in geological terms. But the mechanism, the exact sequence of events that turned chemistry into something that could eat, grow, reproduce and evolve, remains a mystery. What we do know is that once it started, it did not stop. Life spread, it adapted. It survived multiple mass extinctions, ice ages, asteroid impacts, volcanic eruptions that blacked out the sky for years. It filled every available niche, from boiling hydrothermal vents at the bottom of the ocean to frozen valleys in Antarctica where nothing should be able to survive. And over billions of years, through a process so slow and so patient that no human mind can fully grasp it, that life became us. We are made of atoms forged in the cores of dying stars. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, none of it existed in the early universe. Hydrogen and helium, yes. Trace amounts of lithium, fine. But everything heavier had to be built inside stars, fused together under the crushing pressure and heat of nuclear fusion, and then scattered into space when those stars exploded. The Sun is a second or third generation star, formed from a cloud of gas that had already been enriched by earlier generations of stellar death. The planets, including Earth, are made from the leftovers. We are, quite literally, made of stardust. That is not poetry, that is chemistry. And the conditions that allow us to exist here are absurdly specific. Earth sits in what astronomers call the habitable zone, the narrow band of distances from a star where temperatures allow liquid water to exist on a planet's surface. Too close and the water boils away, too far and it freezes. Earth sits right in the middle. Our atmosphere is thick enough to hold heat, but not so thick that it traps it like Venus, where surface temperatures reach 470 degrees Celsius. We have a magnetic field generated by a molten iron core, which shields us from the solar wind that would otherwise strip away our atmosphere over millions of years. We have a moon, unusually large for a planet our size, which stabilizes our axial tilt and prevents wild climate swings. We have plate tectonics, which recycle carbon and regulate the climate over geological timescales. We orbit a star that is stable, long-lived, and not prone to violent flares. And we have had 4.5 billion years of relative peace in a galaxy that is not particularly peaceful. All of that had to line up, and it did. Against odds we still cannot calculate with any confidence. The fact that you are reading this, that you have a brain capable of contemplating your own existence, that you are a pattern of matter complex enough to ask where you came from and what it all means, is so statistically improbable that if the universe were not as large as it is, it might never have happened at all. Our Sun is one star among hundreds of billions in the Milky Way galaxy. It is not special. It is a yellow dwarf, a G-type main sequence star, about halfway through its 10 billion year lifespan. It formed 4.5 billion years ago from a collapsing cloud of gas and dust in the Orion Spur, a minor spiral arm on the outskirts of the galaxy. It burns hydrogen into helium in its core, releasing energy in the form of light and heat. That light takes 8 minutes to reach Earth. It warms the surface, drives the weather, powers photosynthesis, and makes life possible. Without the sun, Earth would be a frozen rock drifting through the dark. In about 5 billion years, the sun will exhaust its hydrogen fuel. Its core will contract and heat up, causing the outer layers to expand. It will become a red giant, swelling to roughly the orbit of Mars. Earth will either be consumed or left as a charred cinder orbiting a dying star. Eventually, the sun will shed its outer layers, leaving behind a white dwarf, a dense cooling ember roughly the size of Earth. That white dwarf will radiate heat for trillions of years, slowly fading until it becomes a black dwarf, a dark, cold remnant that no longer emits light. But we will not be here to see it. Life on Earth, if it still exists in any form, has maybe another billion years before the increasing luminosity of the aging sun makes the planet uninhabitable. So we have a cosmic address. Earth, third planet from the sun. Solar system, located in the Orion spur of the Milky Way galaxy. Milky Way, a barred spiral galaxy, roughly 100,000 light-years across, containing between 200 and 400 billion stars. Local group, a collection of more than 50 galaxies, including the Milky Way, Andromeda, and Triangulum. Virgo supercluster, a massive structure containing thousands of galaxies spanning over 100 million light-years. Laniakea supercluster, an even larger structure containing the Virgo supercluster and others, defining the gravitational basin in which our galaxy resides. Observable universe, a sphere roughly 93 billion light-years in diameter, containing an estimated 200 billion galaxies, each with hundreds of billions of stars. That is where we are. That is the full mailing address. And at no point in that address does Earth show up as anything other than a rounding error. Here is the thing that keeps cosmologists awake at night. We do not know if we are alone. We have found no evidence of life anywhere else in the universe. Not a single microbe, not a radio signal, not a chemical signature in the atmosphere of an exoplanet that cannot be explained by geology. The universe is enormous and old and filled with places where life could exist. And yet, as far as we can tell, we are the only ones looking back. That is either because life is so rare that it has only happened once in this corner of the universe, or because it happens all the time, but intelligence is the bottleneck, or because intelligence happens but destroys itself before it gets far, or because we are not looking in the right way, or because the universe is so large and communication so slow that we are simply shouting into an empty room and will not hear an answer for millennia. None of those possibilities are comforting. If we are alone, the responsibility is staggering. If we are not, the silence is terrifying. The pale blue dot is not just a photograph, it is a reminder. A reminder that everything we have ever known exists on a fragile world, suspended in an unimaginably vast and indifferent cosmos. That our planet is not the center of anything. That the universe was here long before us and will be here long after. That the distances between stars are so large that light itself, the fastest thing in existence, takes years to cross them. That we are newcomers, an experiment still in progress, a species that has existed for a few 100,000 years on a planet that has existed for 4.5 billion, in a universe that has existed for nearly 14 billion. We have been here for the blink of an eye, and we have no guarantee of tomorrow. But we are here now. Against impossible odds, we are here, conscious, curious, capable of looking out into the dark and asking what else is out there, capable of building machines that can travel to the edge of the solar system and turn around to take a picture, capable of understanding, at least in part, where we came from and where we are going. That is worth something. That might be worth everything. The Milky Way stretches across the night sky like a river of light. To our ancestors, it was a mystery, a glowing band they could not explain. Now we know what it is. It is home, our island in the cosmic ocean, and it is time to take a closer look. We call it the Milky Way because when you look up on a clear night far from city lights, it looks like someone spilled milk across the sky. A glowing river of light stretching from horizon to horizon, so thick with stars that your eyes cannot separate them into individual points. Ancient cultures saw different things in that band. The Greeks thought it was milk sprayed from the breast of the goddess Hera. The Chinese called it the Silver River. The Finns believed it was the path birds took to migrate south in winter. The Maori saw it as the canoe of their ancestor. Every culture looked up and told a story about what that light meant. None of them knew what it actually was. Galileo figured it out in 1610. He pointed his telescope at the Milky Way and saw that the glow was not continuous. It was made of stars. Thousands of them, packed so densely that to the naked eye they blurred together into a luminous haze. That was the first hint. The full answer took another 3 centuries. The Milky Way is not a river of spilled milk or a divine artifact. It is a galaxy, a massive rotating system of stars, gas, dust, and dark matter held together by gravity, shaped by rotation, aged by time, and governed by physics that took until the 20th century to understand. It is home. Our island in a cosmic ocean that contains hundreds of billions of other islands just like it. And for most of human history, we did not even know we lived on an island at all. By the early 1900s, astronomers had started mapping the distribution of stars around us and realized we were sitting inside something much larger than anyone had guessed. The debate at the time was whether the Milky Way was the entire universe or just one galaxy among many. In 1920, 2 astronomers named Harlow Shapley and Heber Curtis held what became known as the Great Debate. Shapley argued that the Milky Way was enormous and that the fuzzy spiral nebulae scattered across the sky were just clouds of gas inside it. Curtis argued the opposite, that those spirals were distant galaxies and the Milky Way was just one of many. Curtis was right. But it took Edwin Hubble to prove it in 1923 when he identified Cepheid variable stars in the Andromeda Nebula and calculated that it was nearly 1 million light-years away, far too distant to be part of our galaxy. The Milky Way was not the universe, it was a galaxy, one of countless others drifting through the void. And once we knew that, the next question was obvious. What does our galaxy actually look like? We cannot step outside and take a picture. We are embedded in the disk, surrounded by stars and dust, like trying to map the shape of a forest while standing in the middle of it. Every observation we make is from the inside looking out. But over the last century, astronomers have pieced together a picture using radio waves, infrared light, star counts, gas clouds, and the motion of objects orbiting the galactic center. What emerged is a structure more complex than anyone expected. The Milky Way is a barred spiral galaxy. That means it has a central bar-shaped region made of densely packed stars, with spiral arms winding outward from the ends of that bar. For a long time, astronomers thought we were a pure spiral with 4 major arms wrapping symmetrically around a circular core. Then better observations revealed the bar. And then newer data from the Gaia satellite, a European spacecraft that has been measuring the positions and motions of over 1 billion stars with absurd precision since 2013, forced another revision. The Milky Way does not have 4 major spiral arms, it has 2, Scutum Centaurus and Perseus. The other two arms we thought were major, Norma and Sagittarius, are actually minor arms, smaller and less defined, fragments rather than full structures. Spiral arms are not solid objects, they are density waves. Think of traffic on a highway. Cars bunch up in certain areas, not because the road is narrower there, but because the flow of vehicles creates temporary clusters that move as a wave. Stars and gas clouds behave the same way in a galaxy. They flow through the spiral arms, slow down slightly as they pass through the denser regions, and then continue on. The arms themselves persist even as individual stars move in and out of them. The spiral pattern rotates more slowly than the stars do. It is a pattern, not a thing, a shape carved into the distribution of matter by gravity and rotation. The bar at the center is different. That is an actual concentration of stars, a thick, elongated bulge, roughly 27,000 light-years long. Bars form in spiral galaxies when instabilities in the rotating disk cause stars near the center to settle into elongated orbits. Once a bar forms, it funnels gas toward the center, feeding star formation and sometimes feeding the supermassive black hole that sits at the core of nearly every large galaxy. Our bar has been around for billions of years and shows no sign of going anywhere. The whole structure is embedded in a much larger halo, a roughly spherical cloud of old stars, globular clusters, and dark matter that extends hundreds of thousands of light-years beyond the visible disk. The halo contains some of the oldest stars in the galaxy, fossils from the early days of the Milky Way's formation. Those stars are metal-poor, meaning they contain very few elements heavier than hydrogen and helium, because they formed before generations of earlier stars had lived and died and enriched the galaxy with heavier elements. The halo is where you go to study the ancient past. The disk itself, where most of the action happens, is about 100,000 light-years across. That is the number you see in most textbooks. 100,000 light-years from edge to edge. 1 light-year, just to ground that, is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. In 1 year, it covers roughly 9.5 trillion kilometers per second. In 1 year, it covers roughly 9.5 trillion kilometers. Multiply that by 100,000 and you get the diameter of the Milky Way. It is not a distance your brain can process in any meaningful way. Walking across the galaxy at a steady pace of 5 kilometers per hour would take you about 200 billion years. The universe is only 13.8 billion years old. You could not walk across the Milky Way in the time the universe has existed, even if you started walking the moment the Big Bang happened. The disk is not flat, it is warped, twisted at the edges like the brim of a hat that someone sat on. We do not know exactly why. It might be the gravitational influence of the Magellanic Clouds, 2 small satellite galaxies orbiting the Milky Way, tugging on the outer disk as they pass. It might be leftover distortion from an ancient collision with another galaxy. The warp is subtle but measurable, and it shows that even a structure as massive as a galaxy is not rigid. It flexes, it bends. It responds to forces acting on it over millions of years. And then there are the stars, somewhere between 100 billion and 400 billion of them. That range is wide because counting stars in a galaxy is harder than it sounds. You cannot just point a telescope at the sky and start tallying. Most stars are too faint to see individually from a distance. The Milky Way contains a huge population of red dwarfs, small dim stars that can burn for trillions of years but are so faint that we have only recently started detecting them in large numbers. There are also brown dwarfs, objects too small to sustain hydrogen fusion, halfway between a planet and a star. Those do not show up in most surveys at all. Early estimates put the total star count at around 100 billion because that was a nice round number and roughly consistent with the brightness of the galaxy. But modern models, accounting for the full population of dim low-mass stars, push the number closer to 400 billion. Either way, the Milky Way contains more stars than there are grains of sand on every beach on Earth, and that is just one galaxy. Our Sun sits about 25 to 27,000 light-years from the galactic center, depending on which measurement you trust. That puts us in the Orion Arm, a small partial arm sometimes called the Orion Spur, which branches off between the larger Sagittarius and Perseus arms. We are not in the center. We are not even in one of the major arms. We are in a side branch, out in the suburbs, orbiting the galactic core at a speed of about 220 kilometers per second. At that speed, it takes the Sun roughly 250 million years to complete one orbit around the galaxy. The last time we were in this part of the galaxy, dinosaurs had just started to appear on Earth. The next time we come around, if Earth still exists, the continents will have moved, the stars in the night sky will be completely rearranged, and the Sun will be noticeably older and hotter. That orbital period is called a galactic year. We have completed about 20 of them since the Sun formed 4.5 billion years ago. In all that time, the solar system has been riding a relatively smooth path through the disk, avoiding the dense, chaotic regions near the center, staying clear of the most violent star-forming regions, threading a quiet route through the spiral arms where the radiation levels are low and the risk of close encounters with other stars is minimal. That stability matters. If we were closer to the center, the density of stars would be much higher, increasing the chances of gravitational disruptions that could fling planets out of their orbits or send comets raining into the inner solar system. If we were in a more active star-forming region, the radiation from nearby supernovae could strip away Earth's ozone layer and sterilize the surface. We are where we are not by accident, but because this is one of the few places in the galaxy where life could survive long enough to evolve into something capable of asking why. And there is another benefit to our location. We can see out. The center of the Milky Way is a mess. It is crowded, dusty, and obscured by clouds of gas that block visible light. If Earth were located closer to the core, our view of the rest of the universe would be severely limited. We would be looking through a fog. Instead, we are out on the edge where the dust thins out and the line of sight to distant galaxies is relatively clear. That has been an enormous advantage for astronomy. The fact that we can see the cosmic microwave background, map distant galaxy clusters, and detect the faint light from objects billions of light-years away is partly due to the fact that we happen to be in one of the clearest parts of the Milky Way. We are in the cheap seats, far from the action, but the view is spectacular. At the very center of the galaxy, buried beneath all that dust, sits something we cannot see directly, but know is there. Sagittarius A star, a supermassive black hole weighing about 4 million times the mass of the Sun. For years, astronomers tracked the orbits of stars near the galactic center and watched them whip around an invisible point at speeds that could only be explained by an enormous concentration of mass in a very small space. Some of those stars complete their orbits in less than 20 years, reaching speeds of several percent the speed of light as they swing past the black hole. The precision of those measurements was good enough to win the Nobel Prize in Physics in 2020 for Andrea Ghez and Reinhard Genzel, who led the teams that mapped the orbits. Sagittarius A star does not emit light, it is a black hole. But the region around it glows faintly in radio and infrared wavelengths from the hot gas and radiation being flung around by the black hole's gravity. In 2022, the Event Horizon Telescope, a global network of radio dishes working together as a single Earth-sized telescope, released the first image of Sagittarius A star. Not the black hole itself, which is by definition invisible, but the glowing ring of superheated matter orbiting just outside the event horizon. The image looks almost identical to the earlier image of the black hole in the center of the galaxy Messier 87, confirming that supermassive black holes, despite their different sizes and environments, behave exactly the way Einstein's equations predict. The black hole at our galactic center is quiet. It is not feeding aggressively. There is no massive accretion disk, no jets of radiation blasting out into space. Sagittarius A star is, by supermassive black hole standards, dormant. That was not always the case. Evidence suggests that a few million years ago, the black hole went through an active phase, consuming a large amount of gas and lighting up the center of the galaxy. We see the afterglow of that event in the form of two enormous bubbles of X-ray and gamma-ray emission extending tens of thousands of light-years above and below the galactic plane. They are called the Fermi bubbles, named after the Fermi Gamma-ray Space Telescope that discovered them in 2010. Nobody knows exactly what caused them, but the leading explanation is that Sagittarius A star swallowed something big a few million years ago, burped, and blew those bubbles into the surrounding space. They are still expanding. They will fade over millions of years. And by the time they do, Sagittarius A star might wake up again. The spiral arms, the bar, the halo, the black hole, all of it is held together by something we cannot see. Dark matter. The Milky Way, like every other galaxy we have observed, is embedded in a halo of dark matter that outweighs all the stars, gas and dust combined by a factor of about 10 to 1. We know it is there because the outer parts of the galaxy are rotating too fast. Stars far from the center should be moving slower, the way outer planets in a solar system move slower than inner planets. But they are not. They are moving just as fast as stars closer in, which means there is extra mass out there pulling on them, mass we cannot see. That mass is dark matter. We do not know what it is made of. We have never detected a dark matter particle directly. But the gravitational effects are undeniable. The Milky Way is not just a collection of stars. It is a structure carved out of dark matter, with ordinary matter filling in the details. Then there is the mystery of the spiral arms themselves. New data from the Gaia satellite has revealed something unexpected. The spiral arms are not permanent. They are transient features that last only about 80 to 100 million years before they dissolve and reform. That is a tiny fraction of the galaxy's age. The Milky Way is roughly 13 billion years old. The spiral arms we see today are not the same arms that existed when the dinosaurs walked the Earth. They are not the same arms that will be here when the sun becomes a red giant. They come and go, shaped by density waves that ripple through the disk like sound waves through air. The pattern persists, but the details change. Spiral structure typically emerges about 3.6 billion years after a galaxy forms, driven by differential rotation and gravitational instabilities. The Milky Way's arms are stronger in magnetic fields than the rest of the disk, with field strengths of about 25 microgas compared to 10 microgas in the interarm regions. Those magnetic fields help channel gas into the arms and trigger star formation. Young hot stars light up the arms, making them visible across intergalactic distances. But the stars do not stay in the arms. They drift out, age, dim, and eventually die. The arms themselves move on, gathering new material, forming new stars, maintaining the pattern even as the individual pieces change. All of this, the structure, the rotation, the black hole, the dark matter halo, the transient spiral arms, has been mapped from the inside. We are stuck in the disk, 25,000 light-years from the center, trying to reconstruct the shape of the galaxy from our limited vantage point. It is like trying to draw a map of a city while standing in the middle of it with a blindfold on, using only the sounds you hear and the motion of traffic around you. The fact that we have managed to build an accurate picture at all is a testament to human ingenuity and the power of modern instruments. But here is the uncomfortable part. The Milky Way is ordinary. There is nothing special about it. It is a mid-sized barred spiral galaxy in a quiet part of the universe. It is not the biggest galaxy we have ever found. It is not the brightest. It is not the oldest or the youngest or the most active. It is average, and that is the point. The Milky Way is what a typical galaxy looks like after 13 billion years of evolution. It has grown by merging with smaller galaxies, some of which are still visible as streams of stars being pulled apart by tidal forces. It has formed stars in bursts and lulls, depending on how much gas was available. It has a supermassive black hole at its center, because every large galaxy has one, and it will eventually collide with the Andromeda Galaxy in about 4 billion years, merging into a larger elliptical galaxy that future astronomers, if they exist, will give a new name. We live in the Milky Way not because it is unique, but because it is typical. And that ordinariness is one of the most profound discoveries in the history of astronomy. If our galaxy is average, and if galaxies are common, then the universe is filled with places like this. Billions of galaxies, each containing hundreds of billions of stars, each with the potential to host planets, and on some of those planets, maybe, life. But before we can explore those other galaxies, we had to map our own. And now that we have, the view has changed. The Milky Way is no longer a glowing band of mysterious light stretched across the night sky. It is a structure, a galaxy, an island 100,000 light-years across, containing hundreds of billions of stars, rotating once every few 100 million years, shaped by forces we are only beginning to understand. It is home, and it is time to look beyond it. The Milky Way is not alone. That might seem obvious now, but for most of human history, it was not obvious at all. For thousands of years, the glowing band across the night sky was the entire known universe. Everything we could see, every star, every nebula, every faint smudge of light, was assumed to be part of one vast cosmic structure, with Earth somewhere near the middle. The idea that there might be other galaxies, other islands of stars, separated from ours by gulfs of empty space so vast that light itself took millions of years to cross them, was not even on the table. It was not that people were stupid. It was that the tools did not exist to see that far, and the mathematics to interpret what those tools would eventually show had not been invented yet. By the early 20th century, astronomers had catalogued thousands of fuzzy objects scattered across the sky. They called them nebulae, Latin for clouds, because that is what they looked like through the telescopes of the time. Faint, indistinct patches of light that did not resolve into individual stars, no matter how much magnification you threw at them. Some nebulae were clearly part of the Milky Way. The Orion Nebula, for example, was obviously a cloud of glowing gas lit up by nearby stars. But others were different. They had a spiral structure, a symmetry, an appearance that suggested something more organized than a random cloud. What were they? Two camps formed. One side, led by astronomers like Harlow Shapley, argued that these spiral nebulae were just unusually shaped gas clouds inside the Milky Way. The Milky Way was enormous, they said, And these nebulae were simply part of it, scattered throughout our galaxy like ornaments on a very large tree. The other side, championed by Heber Curtis and others, argued that the spiral nebulae were separate galaxies, distant island universes far beyond the boundaries of the Milky Way. Both sides had evidence, neither had proof. The debate raged for years, splitting the astronomical community into rival factions that argued bitterly at conferences and in scientific journals. The argument was settled in 1923 by a man named Edwin Hubble, not the telescope, the man the telescope was later named after. Hubble was working at the Mount Wilson Observatory in California, home to the largest telescope in the world at the time, a 100-inch reflector perched on a mountain above Los Angeles. He was studying the Andromeda Nebula, one of the largest and brightest of the spiral nebulae, trying to resolve its structure. And in October of that year, he found something that changed everything. Hubble identified a type of star called a Cepheid variable inside Andromeda. Cepheid variables are stars that pulse, brightening and dimming in a regular rhythm. The key discovery, made a decade earlier by a woman named Henrietta Swan Leavitt, was that the period of that pulsation, how long it takes the star to go from bright to dim and back again, is directly related to how intrinsically luminous the star actually is. Measure the period, and you know the true brightness. Compare the true brightness to how bright the star looks from Earth, and you can calculate how far away it is. It is one of the most powerful distance measurement tools in astronomy, and Hubble used it to measure the distance to Andromeda. The number he got was staggering. Andromeda was not a few thousand light-years away, which would place it comfortably inside the Milky Way. It was roughly 900,000 light-years away. Later measurements revised that number upward to about 2.5 million light-years, but the conclusion was the same. Andromeda was not part of the Milky Way. It was far beyond it. It was another galaxy, an island universe. And if Andromeda was a separate galaxy, then so were all the other spiral nebulae scattered across the sky. The Milky Way was not the universe. It was one galaxy among many. Hubble published his findings in 1925, and the debate was over. Curtis had been right. The universe was vastly larger than anyone had imagined. The Milky Way was just one galaxy in a cosmos filled with them. And once that door opened, the questions came flooding through. How many galaxies are there? How far away are they? Are they all spirals, or are there other shapes? What holds them together, and do they move? Hubble kept working. Over the next few years, he measured the distances to more galaxies and noticed something strange. The farther away a galaxy was, the faster it seemed to be moving away from us. The relationship was linear, double the distance, double the speed. This was not a small effect. Galaxies millions of light-years away were receding at speeds of hundreds of kilometers per second. Galaxies tens of millions of light-years away were moving even faster. The universe was not static, it was expanding. Every galaxy was moving away from every other galaxy, not because they were flying through space like shrapnel from an explosion, but because space itself was expanding, carrying the galaxies along with it. That discovery, published in 1929, laid the foundation for modern cosmology. It gave us the expanding universe. It gave us the Big Bang. It gave us a framework for understanding the large-scale structure of the cosmos. And it started with Hubble staring at a fuzzy patch of light in the Andromeda constellation and asking, how far away is that? The Milky Way sits in a small corner of the universe called the local group. That name is not poetic, it is just a label, the way you might call a neighborhood, a residential zone. The local group is a collection of galaxies bound together by gravity. a small cluster that occupies a region of space roughly 10 million light-years across. That sounds enormous. It is by human standards, but on the scale of the universe, the local group is a speck. It is one of hundreds of thousands of similar groups scattered across the observable cosmos, and it is not even a particularly large or interesting one. The local group contains 3 major galaxies and somewhere between 50 and 130 smaller ones, depending on how you count. The exact number is still uncertain because some of the dwarf galaxies are so faint that we have only recently started detecting them, and others are hidden behind the disk of the Milky Way, where our view is blocked by dust. Galaxies are being added to the census every few years as surveys get deeper and detection methods improve. The 3 big galaxies are the ones that dominate the group. Andromeda is the largest, a massive spiral galaxy containing roughly 1 trillion stars. It is about twice the size of the Milky Way in terms of stellar mass, though recent measurements suggest the 2 galaxies are closer in total mass than we thought, once you account for dark matter. Andromeda is located about 2.5 million light-years from the Milky Way, which makes it the closest large galaxy to us. On a clear, dark night, far from city lights, you can see it with your naked eye as a faint oval smudge in the constellation Andromeda. That smudge is the combined light of 1 trillion stars, photons that left Andromeda 2.5 million years ago when our ancestors were just starting to figure out how to use stone tools. You are looking at ancient light from another galaxy, and you do not need a telescope to do it. The Milky Way is the 2nd largest member of the local group. We have already talked about its structure. Barred spiral, 100,000 light-years across, 2 to 400 billion stars sitting in a halo of dark matter. It is our home, and it is ordinary. There is nothing about the Milky Way that makes it special compared to other spiral galaxies of similar size. It has the same kinds of stars, the same kinds of nebulae, the same supermassive black hole at the center. If you were observing the local group from another galaxy cluster 100 million light-years away, the Milky Way would be just another spiral, unremarkable except for the fact that it happens to host at least one species capable of asking questions about the universe. The 3rd major galaxy is Triangulum, also known as Messier 33. Triangulum is smaller than the Milky Way and Andromeda, weighing in at around 40 billion stars. It is a spiral galaxy, but it does not have a central bar like the Milky Way does. It is located about 3 million light-years from us, and like Andromeda, it is visible to the naked eye under very dark skies, though it is much fainter and harder to spot. Triangulum is the 3rd largest galaxy in the local group, and depending on whose model you believe, it may or may not be gravitationally bound to Andromeda. Some simulations suggest it is orbiting Andromeda. Others suggest it is just passing through the local group and will eventually escape. The data is not clear enough to say for sure. Then there are the dwarfs. Dozens of them, scattered throughout the local group like moons around a planet. These are small galaxies, some containing only a few million stars, others with a few billion. Most of them are irregular in shape, lacking the organized structure of spirals or ellipticals. They are faint, difficult to detect, and easy to overlook, but they matter. Dwarf galaxies are the most common type of galaxy in the universe. For every large spiral, like the Milky Way or Andromeda, there are dozens or hundreds of dwarfs. They are the building blocks of larger galaxies, the leftovers from the early universe, and in some cases, the fossils of galaxies that were torn apart by tidal forces. 2 of the most famous dwarf galaxies are the Large and Small Magellanic Clouds, visible from the southern hemisphere as 2 bright patches in the night sky. They are irregular galaxies orbiting the Milky Way, close enough that their gravity is pulling streams of gas off their surfaces and funneling it into our galaxy. The Large Magellanic Cloud is about 160,000 light-years away and contains roughly 30 billion stars. The Small Magellanic Cloud is slightly farther and smaller. Both are being slowly devoured by the Milky Way. In a few billion years, they will be completely absorbed, their stars scattered throughout our galaxy, their structure erased. That process is happening right now. It is not violent. It is not sudden. It is just gravity doing what gravity does, pulling things together over timescales so long that entire civilizations could rise and fall without noticing the change. Recent models suggest that the Magellanic Clouds did not just drift peacefully into the Milky Way's neighborhood. They collided head-on with each other a few 100 million years ago, a violent encounter that distorted their shapes and sent shockwaves rippling through their gas clouds, triggering bursts of star formation. That collision is why they look irregular today. They used to be more organized, possibly even small spiral galaxies, but the impact scrambled their structure. Now they are accelerating toward the Milky Way, and within a few 100 million years they will merge with it. Their stars will become our stars. Their gas will feed new generations of stars in the Milky Way's disk, and the Magellanic Clouds will cease to exist as separate objects. Other dwarfs in the local group are even smaller and fainter. Galaxies like Draco, Ursa Minor, and Sculptor are so dim that they were not discovered until the mid-20th century, and even then, only because astronomers started using sensitive photographic plates to map faint objects in the sky. These ultra-faint dwarfs contain only a few thousand to a few 100,000 stars, making them barely more luminous than a single globular cluster. They are the ghosts of galaxies, held together more by dark matter than by the gravity of their stars. In fact, some of these dwarfs are the most dark matter-dominated objects in the universe. Up to 99% of their mass is dark matter, with only a tiny fraction in the form of visible stars. Why does the local group exist? Why are these galaxies bound together while others are flying apart? The answer is gravity and timing. In the early universe, matter was distributed almost uniformly, with only tiny density fluctuations, slight over-densities where there was a bit more matter than average. Over time, gravity amplified those over-densities. Regions with slightly more matter attracted more matter. Those regions grew denser, pulled in surrounding gas and dark matter, and eventually collapsed into the first galaxies. Galaxies that formed near each other within a few million light-years became gravitationally bound. They formed groups. The local group is one of those bound systems, a small collection of galaxies that will never escape each other. They are stuck together, orbiting a common center of mass, slowly merging over billions of years. The local group is part of a much larger structure called the Laniakea supercluster, a vast collection of galaxy groups and clusters spanning more than 500 million light-years. At the heart of Laniakea sits the Virgo cluster, a massive concentration of galaxies about 70 million light-years from the Milky Way. The Virgo cluster contains over 1,000 galaxies, far more than the local group, and its gravity is pulling the local group toward it at a speed of several hundred kilometers per second. We are falling toward Virgo. We have been falling for billions of years, and we will continue to fall for billions more. On the largest scales, galaxies do not just sit still. They move, they flow. They are pulled by the gravity of larger structures, accelerated by the expansion of space, and swept into vast cosmic currents that shape the distribution of matter across the universe. But the local group is just the beginning. Beyond it lie billions of other galaxies, scattered across the observable universe like grains of sand on an endless beach. How many galaxies are there? That is one of the most important questions in cosmology, and the answer has changed as our instruments have improved. In the 1990s, the Hubble Space Telescope conducted a survey called the Hubble Deep Field. Astronomers pointed the telescope at a tiny patch of sky, a region so small it would be covered by a grain of sand held at arm's length, and stared at it for 10 days. When they processed the images, they found roughly 3,000 galaxies in that single patch. Most of them were faint, distant, and had never been seen before. The implication was staggering. If a tiny random patch of sky contained 3,000 galaxies, and the sky has millions of such patches, then the total number of galaxies in the observable universe must be enormous. Further surveys refined the estimate. The Hubble Ultra Deep Field, conducted in 2004, went even deeper, revealing galaxies so faint and so distant that their light had been traveling toward us for over 13 billion years. The images showed galaxies as they existed when the universe was less than 1 billion years old, infant galaxies still in the process of forming their first stars. By counting galaxies in these deep fields and extrapolating across the entire sky, astronomers arrived at an estimate: 200 billion galaxies in the observable universe. Some estimates go higher, pushing toward 2 trillion if you account for faint dwarf galaxies that are too dim to detect individually. But 200 billion is the number that has stuck, the figure most textbooks cite, the one that gives you a sense of scale without overwhelming the brain completely. 200 billion galaxies, each containing anywhere from a few million to several trillion stars, each separated from its neighbors by millions of light years of mostly empty space, each evolving on its own timeline, forming stars, swallowing gas, colliding with neighbors, spinning through the void according to the laws of gravity and the push of dark energy. The variety is staggering. Galaxies come in every shape and size. Spirals like the Milky Way and Andromeda, with graceful arms winding outward from a central bulge. Ellipticals, smooth, featureless blobs of old stars with little gas or dust left to form new ones. Irregulars like the Magellanic Clouds, chaotic and asymmetric, often the result of collisions or gravitational interactions. Ring galaxies, where a smaller galaxy has punched through the center of a larger one, sending a shockwave rippling outward and triggering a ring of star formation. Lenticular galaxies, which sit somewhere between spirals and ellipticals, with a disk but no spiral arms. And then there are the peculiar galaxies, objects so distorted by tidal forces or past collisions that they do not fit into any neat category. Galaxies with tails, bridges of stars stretching between two merging systems. Galaxies with shells, faint arcs of stars wrapped around a central core. Galaxies that look like jellyfish, their gas being stripped away as they fall through galaxy clusters at high speed. The classification of galaxies began with Edwin Hubble, who developed a system known as the Hubble sequence, or the tuning fork diagram. Ellipticals on one side, spirals on the other, with lenticulars in the middle. For decades, astronomers used that classification to organize the zoo of galaxies they were discovering. But as observations improved, the system started to show cracks. Galaxies do not fit neatly into boxes. They merge, evolve, and transform over time. A spiral today might be an elliptical tomorrow after it collides with a neighbor. A dwarf irregular might have once been a spiral before tidal forces tore it apart. The Hubble sequence is still useful as a rough guide, but it is not the final word. Galaxies are messier than any classification scheme can capture. What holds a galaxy together? The obvious answer is gravity. Stars orbit the galactic center because they are pulled inward by the combined mass of all the other stars, gas and dark matter in the galaxy. But the details are more complicated. Stars in a galaxy do not orbit the way planets orbit a sun. Planets follow smooth elliptical paths dictated by a single central mass. Stars in a galaxy are influenced by the gravity of every other star around them, creating a constantly shifting gravitational field. The result is a chaotic dance where individual orbits are irregular and unpredictable over long timescales. Some stars move in nearly circular orbits around the galactic center. Others follow elongated ellipses that carry them out into the halo and back again. And a few stars, the hypervelocity stars, are moving so fast that they will eventually escape the galaxy entirely, flung outward by gravitational interactions with the supermassive black hole at the center, or by close encounters with other stars. Dark matter plays a crucial role. Observations of galaxy rotation curves, measurements of how fast stars are moving at different distances from the galactic center, show that galaxies are spinning too fast to be held together by the gravity of their visible matter alone. Stars in the outer regions of galaxies are moving just as fast as stars closer in, which should not be possible if the only mass present is what we can see. The only explanation that fits the data is that galaxies are embedded in massive halos of dark matter, invisible mass that exerts gravity but does not emit light. The dark matter halo extends far beyond the visible disk, sometimes reaching hundreds of thousands of light years from the center. It is the scaffolding that holds the galaxy together, the hidden foundation that keeps stars from flying off into space. And then there is the question of how galaxies move relative to each other. Hubble showed that the universe is expanding, that distant galaxies are receding from us at speeds proportional to their distance, but the expansion is not perfectly smooth. Galaxies are not spread uniformly across space like dots on a grid. They cluster. They form groups, clusters, superclusters, vast filaments, and walls of galaxies separated by enormous voids where almost nothing exists. The structure is often compared to a cosmic web, a three-dimensional network of matter with galaxies strung along the filaments like beads on a thread. The expansion of the universe stretches the voids and pulls galaxy clusters farther apart. But within clusters, gravity wins. Galaxies in a cluster are bound to each other, orbiting a common center, and will eventually merge over timescales of billions of years. The Milky Way and Andromeda are on a collision course. They are moving toward each other at a speed of about 110 to 123 kilometers per second. In roughly 3 to 4.5 billion years, they will collide. That does not mean stars will smash into each other. Stars are so small and so far apart that even during a galactic collision, direct stellar collisions are extremely rare. What will happen is that the two galaxies will pass through each other, their gravitational fields tangling together, pulling stars and gas into chaotic new orbits. The galaxies will swing past each other, slow down, turn around, and collide again. Over hundreds of millions of years, they will merge, their disks disrupted, their spiral structure destroyed, their gas clouds shocked and compressed, triggering a burst of star formation so intense that the merged galaxy will briefly shine brighter than either galaxy did alone. The final product will be a giant elliptical galaxy, a smooth blob of old stars with little gas left to form new ones. Astronomers have already given it a nickname, Milky Way. Triangulum might join the merger, or it might not. The simulations are not clear. Some models show Triangulum colliding with Andromeda before the Milky Way gets there. Others show it escaping the local group entirely. Either way, the local group as it exists today is temporary. In a few billion years, it will look completely different. The Milky Way will be gone, Andromeda will be gone, Triangulum, the Magellanic Clouds, the dwarf galaxies, all of them will be absorbed or scattered. What will remain is a single giant elliptical galaxy drifting through space, its stars slowly aging, its gas supply exhausted, its star formation history sealed in the distribution of old red stars that make up its body. That is the fate of the local group. But the local group is just one small corner of a universe filled with 200 billion galaxies, each with its own story, its own history, its own fate. The universe is not a static place, it is a work in progress. Galaxies form, grow, collide, merge, and eventually fade as their stars burn out and the universe expands around them. Understanding how that process works, how galaxies are born, and how they evolve is the next step. And that requires looking backward in time, all the way to the early universe, to see how the first galaxies formed in the first place. Start with nothing. Not literally nothing, but close. The early universe, about 400,000 years after the Big Bang, was a hot uniform fog of hydrogen and helium. No stars, no galaxies, no structure at all, just gas, almost perfectly smooth, cooling as the universe expanded. The temperature had dropped enough for electrons and protons to combine into neutral hydrogen atoms, and for the first time since the Big Bang, light could travel freely through space without being scattered by free electrons. That moment is called recombination, and it is when the universe became transparent. The light from that era has been stretched by cosmic expansion into microwave radiation, and we can still detect it today as the cosmic microwave background, a faint glow coming from every direction in the sky, the oldest light in the universe. The CMB is not perfectly smooth. It has tiny temperature fluctuations, variations of about 1 part in 100,000. Those fluctuations are the seeds of everything that came after. Regions that were slightly denser than average had slightly more gravity. That extra gravity pulled in more matter. The denser regions got denser. Over millions of years, those tiny overdensities grew, amplified by gravity, until they collapsed into the first structures. That process is called gravitational instability, and it is how all large-scale structure in the universe formed. Galaxies, galaxy clusters, superclusters, the entire cosmic web, all of it grew from those tiny ripples in the early universe. But here is the problem. The timeline does not work. If you start with hydrogen and helium gas at 400,000 years after the Big Bang and let gravity do its thing, it takes too long. The gas resists collapse because it has pressure. It is hot. It pushes back against gravity. By the time you account for that resistance, the first galaxies should not have formed until the universe was 1 billion years old or more. But observations tell a different story. We have found galaxies that existed when the universe was only a few 100 million years old. Small galaxies, yes, but galaxies nonetheless, with billions of stars already formed. The Standard Model says they should not be there yet. And yet there they are, bright and clear in the data, staring back at us from the edge of time. The solution is dark matter. Dark matter does not have pressure. It does not interact with light or with itself except through gravity. It does not care about temperature, and because it does not interact with radiation, it started collapsing earlier than ordinary matter. While hydrogen and helium were still coupled to photons, held back by radiation pressure, dark matter was already clumping together, forming the first structures, building the scaffolding on which galaxies would eventually assemble. By the time ordinary matter was free to collapse, the dark matter had already done the heavy lifting. It had created deep gravitational wells, dense halos of invisible mass scattered throughout the universe. Ordinary matter fell into those wells, collected at the bottom, cooled, and began forming the first stars. That is the bottom-up model of galaxy formation. Small dark matter halos form first, a few million solar masses each. Gas falls into those halos and forms the first stars, creating small proto-galaxies. Those proto-galaxies merge with each other, building larger and larger structures over time. Small halos combine into bigger halos. Proto-galaxies collide and merge into galaxies. Galaxies merge into larger galaxies. Over billions of years, the process builds the massive galaxies we see today. The Milky Way is the product of hundreds or thousands of smaller mergers, each adding stars and gas to the growing structure. The scars of those ancient collisions are still visible in streams of stars scattered throughout the halo, the remnants of dwarf galaxies that were torn apart and absorbed. There was a competing theory for a while called top-down formation, which suggested that the largest structures formed first and then fragmented into smaller galaxies. That model did not survive contact with the data. Observations show clearly that the smallest galaxies formed first and the largest ones assembled later through mergers. Top-down is dead, bottom-up won. Galaxies grow by eating their neighbors. Dark matter makes up more than 85% of all the matter in the universe. Ordinary matter, the stuff that makes up stars and planets and you, is a minority component. And yet, despite being 5 or 6 times more abundant, dark matter remains invisible. We have never detected a dark matter particle directly. We do not know what it is made of. We know it is there because galaxies rotate too fast to be held together by the gravity of their visible matter alone. We know it is there because galaxy clusters contain far more mass than we can account for by adding up all the stars and gas. We know it is there because the bending of light around massive objects, an effect called gravitational lensing, reveals the presence of enormous concentrations of mass that emit no light. Dark matter is the skeleton of the universe. Ordinary matter is just the flesh draped over it. In November 2024, the James Webb Space Telescope delivered a result that has cosmologists arguing again. Webb looked at some of the earliest galaxies ever observed, galaxies that existed when the universe was less than 1 billion years old, and found that they are too large and too bright. According to the standard lambda-cold dark matter model, those early galaxies should be small and dim, still in the process of assembling from smaller pieces. Instead, they are massive, mature, and shining brightly, as if they had been around for much longer than the universe's age allows. Stacy McGaugh, an astrophysicist at Case Western Reserve University, put it bluntly: what the theory of dark matter predicted is not what we see. That discrepancy has revived interest in an alternative theory called modified Newtonian dynamics, or MOND. MOND proposes that there is no dark matter at all, that what we are seeing is not invisible mass, but a breakdown of Newton's laws of gravity at very low accelerations. In MOND, gravity behaves differently on the scales of galaxies and galaxy clusters, producing the same effects we attribute to dark matter without requiring any new particles. For decades, MOND was dismissed as a fringe idea because it could not explain the full range of observations as well as the dark matter model could. But the Webb data has given it new life. If the earliest galaxies really are too large and too bright to fit the standard model, then maybe we need to reconsider what we think we know about gravity and the structure of the universe. Most astronomers are not ready to abandon dark matter, The standard model explains too many things too well. It predicts the structure of the cosmic microwave background. It explains the formation of galaxy clusters. It matches the observed distribution of galaxies across the universe. Mund struggles with some of those observations, but the tension is real. Something is not adding up, and the Webb data is forcing the field to take a harder look at its assumptions. Dark matter, whether it exists as particles or as a modification of gravity, provided the framework for galaxy formation. But the details of how galaxies actually assembled required something else: a cosmic infrastructure, a network of invisible threads connecting every galaxy to every other galaxy, funneling gas and dark matter along vast highways stretching across hundreds of millions of light years. Astronomers call it the cosmic web, and until recently it was purely theoretical. The cosmic web started forming during the Dark Ages, the period from about 400,000 years after the Big Bang to roughly 50 million years later when the first stars ignited. During that time, dark matter clumped together under gravity, forming filaments, sheets, and nodes. The filaments are long, thin structures, like threads in a spider's web, where dark matter and gas are concentrated. The sheets are flatter regions where filaments intersect. The nodes are the densest points, where multiple filaments cross, and those nodes became the locations of the largest galaxy clusters. Between the filaments lie the voids, vast empty regions containing almost no galaxies, stretching hundreds of millions of light-years across. The cosmic web is not a metaphor. It is a real physical structure carved into the distribution of matter by gravity, and it governs where galaxies form and how they evolve. For decades, astronomers could only infer the existence of the cosmic web by looking at the distribution of galaxies. Galaxies cluster along filaments. They avoid the voids. The large-scale structure of the universe, mapped by galaxy surveys, clearly shows that galaxies are not scattered randomly. They form a web-like pattern. But seeing the web itself, the actual filaments of gas and dark matter connecting galaxies, was impossible. The gas is too diffuse and too cold to emit light. The dark matter is invisible. You could see where the web should be based on where the galaxies are, but you could not see the web directly. In 2024, that changed. A team of astronomers used an instrument called MUSE, mounted on the Very Large Telescope in Chile, to image a cosmic filament directly for the first time. The filament is 3 million light-years long, stretching between galaxies in a region of space about 11 billion light-years from Earth. The detection was made possible by a trick. The filament contains cold hydrogen gas, which normally does not emit light. But the filament is being illuminated by nearby quasars, extremely bright active galactic nuclei powered by supermassive black holes. The ultraviolet light from the quasars excites the hydrogen atoms in the filament, causing them to glow faintly in a specific wavelength. MUSE detected that glow, and for the first time, astronomers had a direct image of a cosmic filament, the connective tissue of the universe, the highway along which gas flows into galaxies. That discovery was labeled a breakthrough. It confirmed what the lambda cold dark matter model had predicted for decades, that the universe is held together by a web of dark matter filaments, and that those filaments funnel gas into galaxies, fueling star formation. Without the cosmic web, galaxies would run out of gas. Star formation would slow and eventually stop as galaxies exhausted their internal reserves, but the web keeps feeding them. Gas from the intergalactic medium, the vast reservoir of diffused hydrogen scattered throughout space, flows along the filaments and into galaxies, providing fresh material for new stars. The process can continue for billions of years, keeping galaxies alive long after they would otherwise have gone quiet. The cosmic web also explains why galaxies cluster. Galaxies form where filaments intersect. The denser the intersection, the more galaxies form. The largest galaxy clusters, containing thousands of galaxies packed into a region a few million light-years across, sit at the nodes of the cosmic web, where multiple filaments converge. The Virgo cluster, the massive concentration of galaxies at the heart of our local supercluster, sits at one of those nodes. So does the Coma cluster, another giant cluster about 300 million light-years away, containing over 1,000 galaxies. These clusters are not random. They are the inevitable result of the web's structure, the places where gravity has concentrated the most matter. The same team that detected the 3 million light-year filament also used the James Webb Space Telescope to study a specific region of the cosmic web in more detail. Webb found a filament containing 10 ancient galaxies and a supermassive black hole, with enough mass to make hundreds of billions of stars. The filament spans roughly 30 times the width of the Milky Way, and it existed when the universe was less than 1 billion years old. That discovery is important because it shows that the cosmic web was already in place very early in the universe's history, guiding the formation of the first galaxies. The web is not a late development. It is a fundamental feature of the universe, present from the beginning, shaping everything that came after. Once gas falls into a dark matter halo and begins to cool, the next step is star formation. Gas clouds collapse under their own gravity. As they collapse, they heat up. When the temperature and density at the core reach a critical threshold, hydrogen nuclei begin fusing into helium. That fusion releases energy, creating radiation pressure that pushes outward, balancing the inward pull of gravity. The cloud stops collapsing. A star is born. That process is happening right now in galaxies all across the universe. In the Milky Way alone, roughly 1 to 3 new stars form every year. In starburst galaxies, regions undergoing intense bursts of star formation triggered by collisions or gas inflows, the rate can be hundreds or thousands of stars per year. Star formation is self-regulating. When a massive star forms, it emits intense ultraviolet radiation that ionizes the surrounding gas, heating it and preventing nearby clouds from collapsing. When the star dies in a supernova, the explosion blows gas out of the galaxy, removing the raw material for future star formation. Those processes, called feedback, limit how quickly a galaxy can turn gas into stars. Without feedback, galaxies would burn through their gas supply in a few 100 million years and then go dark. Feedback slows the process down, stretching star formation out over billions of years. The first stars were different. They formed from pure hydrogen and helium, with no heavier elements. That matters because heavier elements help cool gas clouds, making it easier for them to collapse. Without those elements, the first stars had to form from hotter, more massive clouds, and the result was stars that were enormous, possibly hundreds of times the mass of the Sun. Those stars burned hot and fast, living only a few million years before exploding as supernovae. Their explosions seeded the surrounding gas with the first heavy elements: carbon, oxygen, nitrogen, iron, the building blocks of planets and life. The second generation of stars formed from that enriched gas, and they were smaller, more like the stars we see today. Galaxies do not just grow by forming stars, they grow by merging. A typical galaxy like the Milky Way has experienced hundreds of mergers over its lifetime. Most of those mergers were with small dwarf galaxies, absorbed and digested without much disruption. But occasionally, a galaxy merges with something closer to its own size, and the result is violent. The two galaxies pass through each other, their stars scattered into new orbits, their gas clouds compressed and shocked, triggering massive bursts of star formation. Over hundreds of millions of years, the galaxies merge completely, their cores sinking to the center of the combined system, their stars mixed together into a single larger galaxy. Mergers change a galaxy's appearance. Spiral galaxies are fragile. Their delicate arms and rotating disks are easily disrupted by collisions. When two spirals merge, the result is usually an elliptical galaxy, a smooth, featureless blob with no spiral structure, no disk, and very little gas left to form new stars. Elliptical galaxies are the end state of galaxy evolution, the product of multiple mergers, galaxies that have settled into a stable configuration with no ongoing star formation. They are filled with old red stars, slowly aging toward death. Spirals are young and active, still forming stars, still evolving. Ellipticals are old and quiet, their growth complete. The Milky Way is still a spiral because it has not yet experienced a major merger. It has absorbed plenty of dwarf galaxies, and it is in the process of absorbing the Magellanic Clouds, but those are small snacks that do not disrupt the overall structure. The collision with Andromeda will be different. That will be a major merger, and it will transform both galaxies into a single giant elliptical. The process will take a few billion years, but the outcome is inevitable. The Milky Way's spiral structure will be destroyed, its disk will be scrambled, its gas will be compressed and converted into stars in one final burst of activity. And then the combined galaxy, Milkomeda, will settle into a quiet old age, its star formation history complete, its future nothing but a slow fade as its stars burn out one by one. Galaxies have life cycles. They are born from collapsing clouds of gas and dark matter. They grow by forming stars and merging with neighbors. They mature into stable spirals or ellipticals, and eventually they decline as their gas supplies run out and star formation ceases. The oldest galaxies in the universe, the ones we see in the most distant reaches of space, are young and blue, filled with hot, massive stars burning through their fuel. The galaxies we see nearby, in the local universe, are older and redder, dominated by stars that have been around for billions of years. That color shift, from blue to red, is one of the clearest signs of a galaxy aging. But galaxies do not die, at least not in the way stars do. A galaxy without star formation is still a galaxy. It still contains billions or trillions of stars. Those stars will continue to shine for hundreds of billions of years, slowly fading as they exhaust their fuel. The smallest stars, red dwarfs, can burn for trillions of years, longer than the current age of the universe, by a factor of 100. So even a dead galaxy, one with no gas and no new stars, will remain visible for an almost incomprehensible length of time. The process of galaxy formation and evolution is still being worked out. Every new observation, every new simulation adds detail to the picture. The Webb data showing early galaxies that are too large is just the latest twist in a story that has been unfolding for a century. Galaxies are not simple objects. They are dynamic, evolving systems shaped by gravity, dark matter, star formation, feedback, mergers, and the cosmic web. Understanding how they form and how they change over time is one of the central goals of modern astronomy. And the answer, as with most things in science, is more complicated than anyone expected. The cosmic web connects everything. The dark matter halos provide the scaffolding. The gas flows in along the filaments. Stars form, live and die. Galaxies merge and grow. And the process continues, driven by gravity and the expansion of space, playing out over billions of years across a universe filled with 200 billion galaxies. That is the architecture. But architecture is static. Galaxies are not. They move, they collide, and when they do, the results are spectacular. Galaxies are not islands. That metaphor breaks the moment you realize that islands sit still. Galaxies do not. They orbit, they drift, they fall toward each other. And when two galaxies get close enough, gravity takes over and choreographs one of the most violent and beautiful processes in the universe, a galactic collision, a merger. A dance that takes hundreds of millions of years to complete and reshapes both participants beyond recognition. The word collision is misleading. It conjures images of cars smashing together on a highway, metal crumpling, glass shattering, an instant catastrophe. Galactic collisions are nothing like that. Stars almost never collide. Galaxies are mostly empty space. The Milky Way contains hundreds of billions of stars, but those stars are so small and so far apart that even when two galaxies pass through each other, the odds of any two stars hitting each other are astronomically low. If you could somehow watch a galactic collision from a safe distance, you would not see explosions. You would see two enormous clouds of stars passing through each other like ghosts, their shapes slowly distorting, their structures gradually pulled apart by forces operating on scales so large that individual stars are irrelevant. But gravity does not care about individual stars. Gravity cares about mass. And when two galaxies approach each other, every star, every gas cloud, every particle in one galaxy feels the gravitational pull of every particle in the other. The result is a tidal force, a stretching and squeezing effect that deforms both galaxies, pulling material out into long streamers, compressing gas clouds until they collapse and ignite into new stars, and eventually dragging the two galactic cores toward each other until they merge into a single larger galaxy. The process takes time, hundreds of millions of years, but the outcome is inevitable. Once two galaxies get close enough, once their mutual gravity exceeds the escape velocity, they are locked together. They will merge. There is no avoiding it. The mechanics are straightforward. Gravity is the only force that matters. Two galaxies approach each other, drawn together by their mutual gravitational attraction. As they get closer, the tidal forces increase. Stars on the near side of each galaxy feel a stronger pull than stars on the far side. That difference in gravitational force stretches the galaxies, pulling material out into tidal tails, long strands of stars and gas that trail behind each galaxy like the tail of a comet. The galaxies pass through each other. Their stars do not collide, but their gas clouds do. Gas is different from stars. Gas is diffuse. When two gas clouds slam together at hundreds of kilometers per second, they do not pass through each other. They collide, they compress, they heat up, and if the compression is strong enough, the gas collapses and forms stars. That is where the fireworks happen. The collision compresses gas clouds that were previously stable, pushing them past the threshold where gravity can collapse them into new stars. The result is a starburst, a sudden explosive increase in the rate of star formation. In a typical galaxy like the Milky Way, a few new stars form every year. In a starburst galaxy, that rate can jump by a factor of 100. Hundreds of new stars forming every year, flooding the galaxy with ultraviolet light, ionizing the surrounding gas, heating it to tens of thousands of degrees, lighting up the collision site with a glow visible across millions of light years. Starburst galaxies are among the brightest objects in the universe, not because they are particularly large, but because they are burning through their gas supply at an unsustainable rate. The burst does not last. It cannot. Star formation at that rate exhausts the gas supply in tens of millions of years. The massive stars formed during the starburst live short, violent lives, a few million years at most, and then explode as supernovae. Those explosions blow gas out of the galaxy, removing the raw material for future star formation. The starburst fades, the galaxy goes quiet. What remains is a population of young, hot stars, slowly aging, surrounded by the wreckage of the collision. Long tidal tails of stars stretched across hundreds of thousands of light years, the shredded remnants of two galaxies that no longer exist as separate objects. Not all mergers are created equal. Astronomers distinguish between two types, wet mergers and dry mergers. The names are not poetic, they are descriptive. A wet merger happens when two gas-rich galaxies collide. Gas-rich galaxies are blue, filled with young hot stars still forming from abundant gas clouds. When two blue galaxies merge, the collision compresses their gas, triggering massive starbursts, and the result is a dramatic transformation. Spiral arms are destroyed, disks are scrambled, gas is consumed. The merged galaxy often settles into an elliptical shape, a smooth, featureless blob with no spiral structure and very little gas left. Wet mergers are the ones that make the best pictures. They are bright, messy, and violent. Dry mergers are different. A dry merger happens when two gas-poor galaxies collide. Gas-poor galaxies are red, filled with old stars, their gas supplies exhausted or blown out by earlier episodes of star formation. When two red galaxies merge, there is no gas to compress, no starburst, no dramatic increase in star formation. The galaxies just pass through each other, their stars scattered into new orbits, their structures disrupted, but without the fireworks. Dry mergers are quieter. They do not produce the spectacular images that wet mergers do, but they are just as important. They build the largest elliptical galaxies in the universe, the giant ellipticals at the centers of galaxy clusters, objects containing trillions of stars, assembled over billions of years through dozens or hundreds of dry mergers. The timescale for a complete merger is roughly 500 million years, 500 million years from the first encounter to the final coalescence. That sounds long. It is long by human standards, but on cosmic timescales it is fast. The universe is nearly 14 billion years old. A merger that takes 500 million years is over in less than 4% of the universe's total age, and during those 500 million years, the two galaxies pass through each other multiple times. The first pass distorts both galaxies, pulling out tidal tails, triggering the first starbursts. The galaxies swing past each other, slow down, and turn around. Gravity pulls them back together. They collide again, a second pass, more compression, more star formation, more tidal disruption. They swing past again, slower this time. Eventually, after several passes, the two galactic cores sink to the center of the combined system and merge. The stars from both galaxies are now mixed together. The gas has been consumed or blown out. What remains is a single larger galaxy, the product of the merger, settling into a stable configuration that will persist for billions of years. There are galaxies we can see right now, frozen in the middle of this process. The antennae galaxies, officially catalogued as NGC 4038 and NGC 4039, are two spiral galaxies located about 70 million light-years away in the constellation Corvus. They are in the middle of a merger that began roughly 600 million years ago. The two galaxies have already passed through each other once, and the collision has ripped long tidal tails of stars out of both galaxies, stretching hundreds of thousands of light-years into space. Those tails look like the antennae of an insect, hence the name. The galaxies are bright, glowing with the light of billions of newly formed stars, their cores still distinct but slowly spiraling toward each other. In a few 100 million years, they will merge completely. The tidal tails will fade, the starburst will end, and what will remain is a single elliptical galaxy, the final product of the collision. The Hubble Space Telescope has observed the antennae galaxies in exquisite detail, revealing clusters of young stars scattered throughout the collision zone. Some of those clusters are only 50 million years old, born during the first pass. Others are older, a few 100 million years, formed earlier in the interaction. The clusters are bright, blue, and massive, each containing millions of stars packed into a region a few light years across. They are the direct products of the collision, formed when gas clouds compressed and collapsed during the impact. Over time, those clusters will disperse, their stars scattered by gravitational interactions, and they will become part of the merged galaxy's general stellar population. Another example is the Mice galaxies, NGC 4676, located about 300 million light-years away. Like the antennae, the Mice are two spiral galaxies in the process of merging. The collision has pulled two long tidal tails out of the galaxies, each tail stretching over 300,000 light-years into space. The tails are made of stars, gas and dust, pulled out by tidal forces and left trailing behind the galaxies as they move through space. The name comes from the resemblance to two mice with their tails entangled. The mice are still in the early stages of their merger. The galaxies have not yet passed through each other. They are approaching, their mutual gravity pulling them together, their structures already distorted by tidal forces. In a few 100 million years, they will collide, triggering a starburst, and eventually merge into a single galaxy. These are not isolated cases. Galactic mergers are common. In the nearby universe, about 5% of galaxies are currently involved in interactions. That number was higher in the past. In the early universe, when galaxies were closer together and space had not yet expanded as much, mergers were far more frequent. Many of the large galaxies we see today are the products of multiple ancient mergers, their smooth elliptical shapes the result of billions of years of collisions that erased any trace of their original spiral structure. The Milky Way is not exempt. We are on a collision course with the Andromeda Galaxy. Andromeda is the closest large galaxy to us, located about 2.5 million light-years away, and it is moving toward us at a speed of about 110 kilometers per second. That is not fast by cosmic standards. It is only about 0.04% the speed of light. But it is fast enough. In roughly 4.5 billion years, the Milky Way and Andromeda will collide. The two galaxies will pass through each other, their stars scattering into new orbits, their gas clouds compressing and igniting into starbursts. The collision will not be instantaneous. It will take hundreds of millions of years. The galaxies will pass through each other, swing past, turn around, and collide again. After several passes, their cores will merge, and the two galaxies will settle into a single giant elliptical galaxy. Astronomers have already given it a nickname, Milky Way. The Sun will still be around when that happens. It will have aged, become hotter and brighter, possibly rendering Earth uninhabitable, but the Sun itself will not have reached the red giant phase yet. That happens in about 5 billion years. The collision with Andromeda will occur slightly earlier, around 4.5 billion years from now, but the Sun and its planets will survive the collision. The odds of the solar system being disrupted by a close encounter with another star are low. Stars are so far apart that even during a galactic collision, most of them pass by each other without interacting directly. The solar system will be flung into a new orbit, possibly ejected from the galactic disk entirely and tossed into the halo of the merged galaxy. But the planets will remain bound to the Sun. Life on Earth, if it still exists, will have a very different view of the night sky. The familiar constellations will be gone, replaced by a chaotic swarm of stars as the Milky Way and Andromeda merge. For a few 100 million years, the sky will be filled with bright young stars, the products of the starburst triggered by the collision. And then, as the gas is exhausted and the starburst fades, the sky will grow darker, filled with old red stars, slowly aging, the remnants of two galaxies that no longer exist. Mergers do more than just build larger galaxies. They also feed supermassive black holes. Every large galaxy has a supermassive black hole at its center. The Milky Way has Sagittarius A star, weighing about 4 million solar masses. Andromeda has a black hole roughly 100 million solar masses. When two galaxies merge, their central black holes eventually sink to the center of the merged galaxy and orbit each other, losing energy by emitting gravitational waves and finally merging into a single larger black hole. That process can take hundreds of millions or even billions of years, but the outcome is inevitable. And during the merger, the collision funnels gas toward the galactic center, feeding the black holes, causing them to grow. The black holes become active, accreting gas and emitting enormous amounts of energy in the form of radiation, jets, and winds. That activity lights up the galaxy as a quasar, an active galactic nucleus so bright it can outshine every star in the galaxy combined. Quasars are among the brightest objects in the universe. They are powered by supermassive black holes feeding on gas funneled inward by galaxy mergers. Most quasars existed in the early universe when mergers were more common. By the present day, most large galaxies have gone through their merger phase and settled into stable configurations with dormant black holes. But in the early universe, quasars were everywhere, glowing beacons visible across billions of light years, marking the locations of galaxies in the throes of violent mergers. The merger between the Milky Way and Andromeda will likely produce a quasar. Both galaxies have supermassive black holes. When they merge, gas will be funneled toward the center, feeding the black holes, causing them to light up. For a few million years, the merged galaxy will be an active galactic nucleus, its core blazing with radiation, its jets blasting out into space at nearly the speed of light. And then, as the gas supply runs out, the activity will fade, the black holes will go dormant. The merged galaxy will settle into a quiet old age, its star formation history complete, its future nothing but a slow decline as its stars age and die. Galactic cannibalism is a special case. That is when a large galaxy swallows a much smaller one. The process is less violent than an equal-size merger. The small galaxy is simply torn apart by tidal forces, its stars scattered throughout the larger galaxy. The Milky Way is in the process of cannibalizing the Sagittarius dwarf elliptical galaxy right now. Sagittarius is a small galaxy containing a few billion stars, and it is being pulled apart by the Milky Way's gravity. Long streams of stars from Sagittarius are wrapped around the Milky Way, slowly being absorbed. In a few 100 million years, Sagittarius will no longer exist as a distinct object. Its stars will be part of the Milky Way, indistinguishable from the rest of our galaxy's stellar population. The same fate awaits the Magellanic Clouds, the two small irregular galaxies orbiting the Milky Way. They will eventually be absorbed, their stars added to the Milky Way's total count. Cannibalism is how large galaxies grow. The Milky Way has absorbed dozens, possibly hundreds, of small dwarf galaxies over its lifetime. The evidence is written in streams of stars scattered throughout the halo, the remnants of ancient collisions and absorptions. Each stream is the corpse of a dwarf galaxy that no longer exists, its stars stretched into a long arc by tidal forces, a fossil record of the Milky Way's growth. Not all collisions result in mergers. Sometimes galaxies just graze each other, passing close enough to interact gravitationally, but not close enough to merge. Those interactions can still have dramatic effects. Gas can be stripped out of one or both galaxies. Star formation can be triggered in the tidal tails. The shapes of the galaxies can be distorted, but the galaxies remain separate. They move apart, their encounter over, their futures independent. Those near misses are less common than full mergers, but they happen, and they leave behind clues, distorted shapes, lopsided disks, streams of stars scattered into intergalactic space. The process of galaxy merging has been going on for billions of years. It was more common in the early universe, when galaxies were closer together and space had not yet expanded as much. Back then, the universe was a more crowded place. Galaxies collided and merged constantly, building the large structures we see today. As the universe expanded, galaxies moved farther apart, and the rate of mergers slowed. In the present day, mergers are less common, though they still happen. And in the distant future, as dark energy continues to accelerate the expansion of space, galaxies will move even farther apart. Eventually, the expansion will stretch space so much that galaxies can no longer reach each other. Mergers will stop. The process that has been building larger and larger galaxies over the last 13.5 billion years will reverse. Galaxies will be isolated, drifting alone through an expanding void, unable to interact, unable to merge, slowly fading as their stars burn out and the universe grows cold and dark. But that future is trillions of years away. For now, galaxies still collide, they still merge. The cosmic dance continues. And every collision, every merger, reshapes the universe, building the structures we see today and setting the stage for what comes next. Galaxies are not static. They are dynamic, evolving systems shaped by forces operating on scales so large that entire star clusters are just details in the bigger picture. Gravity drives the process. Time allows it to unfold. And the result is a universe filled with galaxies in every stage of evolution, from young blue spirals, still forming stars, to old red ellipticals that have long since exhausted their gas supplies. The collisions are beautiful. The tidal tails stretched across hundreds of thousands of light years, glowing with the light of newly formed stars, the starbursts lighting up the collision zones. The slow, inexorable merging of two galactic cores into one. It is a process that takes hundreds of millions of years, but the end result is always the same. Two galaxies become one, their structures are erased, their stars are mixed. And the universe has one more elliptical galaxy, one less spiral, one more step toward the final configuration. Gravity choreographs the dance, but gravity is only part of the story. There is something else holding galaxies together, something invisible, something that outweighs all the stars and gas by a factor of 10 to 1. And there is something else pushing space apart, accelerating the expansion, driving galaxies farther from each other with every passing billion years. Those two forces, dark matter and dark energy, are the hidden hand shaping the universe. And understanding them is the next step. Here is the uncomfortable truth. We have no idea what most of the universe is made of, not a vague uncertainty, not a gap in the data that will be filled in once we build a bigger telescope, a complete blank. The matter we can see, the stuff that makes up stars and planets and people, the protons and neutrons and electrons that we have spent centuries studying, accounts for roughly 5% of the total mass energy content of the universe. 5%. The other 95% is something else, something we cannot see, cannot touch, cannot detect directly with any instrument we have ever built. We know it is there because we can see its effects. Galaxies rotate too fast. Galaxy clusters hold together when they should fly apart. Light bends around massive objects that emit no light. The universe is expanding faster than it should. All of that points to the existence of two invisible components that dominate the cosmos: dark matter and dark energy. And despite decades of searching, we still do not know what either of them actually is. The story of dark matter begins with a woman named Vera Rubin staring at data that refused to make sense. It was 1970, and Rubin was an astronomer at the Carnegie Institution in Washington, studying the rotation of spiral galaxies. She was not the first person to notice the problem. A Swiss astronomer named Fritz Zwicky had pointed it out back in the 1930s when he measured the velocities of galaxies in the Coma cluster and realized they were moving too fast. The cluster should have torn itself apart under those speeds, unless there was far more mass holding it together than anyone could see. Zwicky called the missing mass dark matter, but nobody took him seriously. Zwicky was brilliant and abrasive, and had a talent for making enemies. His colleagues dismissed his claim. The problem sat, ignored for 40 years. Rubin brought it back. She was studying the Andromeda galaxy, measuring how fast stars were orbiting at different distances from the galactic center. The expectation was clear. Stars closer to the center, where most of the visible mass is concentrated, should orbit faster. Stars farther out, where the density of stars drops off, should orbit slower. That is how the solar system works. Mercury orbits the Sun faster than Earth. Earth orbits faster than Jupiter. The farther you are from the central mass, the slower you move. Kepler figured that out in the early 1600s. It is one of the oldest and most reliable laws in astronomy. Rubin's data did not follow that law. The stars in the outer regions of Andromeda were moving just as fast as the stars near the center, not slower, the same speed. She checked the data. She ran the observations again. She looked at other galaxies. Same result. Every spiral galaxy she studied showed the same flat rotation curve. Stars at the edge were orbiting way too fast. There was not enough visible mass in those galaxies to hold them together. And yet, they were not flying apart. Something was holding them together. Something with mass. Something that exerted gravity. Something invisible. The implications were staggering. If the rotation curves were flat, if stars at the edge of a galaxy were moving just as fast as stars near the center, then there had to be a massive halo of invisible matter surrounding every galaxy, extending far beyond the visible disk. That halo had to contain more mass than all the stars and gas in the galaxy combined. Without it, the galaxies would tear themselves apart within a few orbits. The fact that galaxies have existed for billions of years, stable and intact, meant the dark matter had to be there. It was not optional. It was required. Rubin published her results in 1970, and the astronomy community collectively gasped. Not because the idea was new. Zwicky had said the same thing 40 years earlier, and a Dutch astronomer named Jan Oort had noticed discrepancies in the motions of stars in the Milky Way back in the 1930s. But Rubin had the data. Clean, precise measurements of galaxy rotation curves that left no room for interpretation. The missing mass was real, and it was everywhere. Since then, the evidence has piled up. Rotation curves are just one line of evidence. There is also gravitational lensing, the bending of light around massive objects. When light from a distant galaxy passes near a massive foreground object, the gravity of that object bends the light, creating distorted images, arcs, or even multiple images of the background galaxy. By measuring how much the light bends, astronomers can calculate how much mass is doing the bending. And again, the numbers do not add up. The amount of bending is far greater than what the visible matter can account for. There is extra mass, invisible mass, contributing to the lensing, dark matter. The cleanest example is the Bullet cluster, two galaxy clusters that collided with each other about 150 million years ago. When the clusters smashed together, the hot gas in each cluster, visible in X-ray observations, slowed down and piled up in the collision zone. Gas is made of ordinary matter. It interacts, it has pressure, it experiences friction. The gas from both clusters collided and stayed behind, but the dark matter did not. Dark matter does not interact with anything except through gravity. It does not have pressure. It does not experience friction. When the two clusters collided, the dark matter halos passed right through each other, unaffected by the collision, and kept moving. Gravitational lensing observations of the Bullet cluster show that the majority of the mass, the stuff doing most of the lensing, is not where the gas is. It is where the dark matter halos are, offset from the collision zone, exactly where you would expect it to be if dark matter is real and behaves the way the models predict. The Bullet cluster is the smoking gun. It is direct observational proof that dark matter exists and that it is something fundamentally different from ordinary matter. How much dark matter is there? The current best estimate, based on measurements of the cosmic microwave background, galaxy surveys, and gravitational lensing, is that dark matter makes up about 27% of the total mass-energy content of the universe. Ordinary matter, the stuff we are made of, is only 5%. Dark matter outweighs ordinary matter by a factor of more than 5 to 1. In individual galaxies, the ratio is even more extreme. More than 95% of the mass in a typical spiral galaxy is dark matter. The stars, the gas, the planets, all of it is just a thin layer of frosting on top of an enormous invisible cake. So what is dark matter? That is the question that has consumed physicists for 50 years, and the honest answer is we do not know. We know what it is not. It is not ordinary matter. It is not made of protons, neutrons, and electrons. If it were, we would be able to detect it. Ordinary matter interacts with light. It emits radiation when it is hot. It absorbs radiation when light passes through it. It glows. Dark matter does none of those things. It is invisible across the entire electromagnetic spectrum. It does not emit light. It does not absorb light. It does not reflect light. The only way we know it exists is through its gravitational influence on things we can see. The leading candidate is something called a WIMP, which stands for Weakly Interacting Massive Particle. The name is not a joke, it is an actual acronym. WIMPs are hypothetical particles that interact only through gravity, and possibly through the weak nuclear force, one of the 4 fundamental forces in nature. They would have mass, which means they would exert gravity, but they would not interact with electromagnetic radiation, which means they would be invisible. WIMPs have never been detected. Dozens of experiments have been built to search for them, deep underground to shield the detectors from cosmic rays, cooled to near absolute zero to reduce thermal noise, waiting for a WIMP to collide with an atomic nucleus and produce a tiny flash of energy. None of those experiments have found anything. After decades of searching, we have no direct evidence that WIMPs exist. Another candidate is the axion, A different hypothetical particle, much lighter than a WIMP, proposed to solve a separate problem in particle physics. Axions would behave like dark matter, clustering in halos around galaxies, contributing to the missing mass. But like WIMPs, axions have never been detected. There are experiments searching for them, trying to convert axions into photons using strong magnetic fields, hoping to catch a signal. So far, nothing. Then there are more exotic ideas. Primordial black holes, tiny black holes that formed in the first fraction of a second after the Big Bang, could account for some of the missing mass. Or maybe dark matter is not made of particles at all. Maybe it is something else entirely, something we have not thought of yet, something that requires new physics to explain. The truth is, we are stuck. We know dark matter is there. We can measure its effects. We can map its distribution using gravitational lensing. We know it forms halos around galaxies, extending out to 200,000 light-years or more from the galactic center. We know it is cold, meaning it moves slowly compared to the speed of light. We know it does not interact with ordinary matter except through gravity. But we do not know what it is, and until we detect a dark matter particle directly or find some other way to probe its nature, we are just guessing. There are a few strange exceptions. Some galaxies seem to have very little dark matter, or possibly none at all. NGC 3379, an elliptical galaxy about 35 million light-years away, has a velocity profile that suggests an absence of dark matter. That is weird. If dark matter is a universal component of galaxies, why does this one not have any? And in 2005, astronomers claimed to have discovered Virgo High 21, a galaxy in the Virgo cluster made almost entirely of dark matter with no visible stars. It was detected only through radio emissions from hydrogen gas. The claim was controversial and has not been fully confirmed, but if it is real, it raises even more questions. If dark matter can clump together and form galaxies on its own without ordinary matter, then what is stopping it from doing that everywhere? Why are most galaxies a mix of dark and ordinary matter? We do not know. Dark matter is the scaffolding that holds the universe together. But there is another invisible component, and it is even stranger: dark energy. If dark matter pulls things together, dark energy pushes them apart, and dark energy is winning. The discovery of dark energy happened almost by accident. In the late 1990s, two independent teams of astronomers were trying to measure how fast the expansion of the universe was slowing down. The universe has been expanding since the Big Bang, and the assumption was that gravity, pulling on everything, would gradually slow that expansion over time. The question was, how much? If there was enough matter in the universe, gravity might eventually stop the expansion and pull everything back together in a big crunch. If there was not enough matter, the universe would expand forever, but the rate of expansion would still slow down. Either way, the expansion should be decelerating. That was the prediction. Both teams used the same method. They observed Type 1a supernovae, a specific type of exploding star that always reaches the same peak brightness. Because the intrinsic brightness is known, you can calculate the distance by measuring how bright the supernova looks from Earth. And because the universe is expanding, light from distant objects is redshifted, stretched to longer wavelengths. By measuring the redshift, you can calculate how fast the object is moving away from us. Put those two pieces of information together, distance and redshift, and you can calculate the expansion rate of the universe at different points in time. If the expansion is slowing down, distant supernovae should be slightly closer than you would expect based on their redshift. If the expansion is speeding up, they should be slightly farther away. The results came in 1998, and they were shocking. The distant supernovae were farther away than expected. Not closer, farther. The expansion was not slowing down, it was speeding up. The universe was accelerating. Something was pushing space apart, overcoming the pull of gravity, driving galaxies farther from each other at an ever-increasing rate. The two teams published their results almost simultaneously, and the cosmology community went into crisis mode. This was not supposed to happen. There was no mechanism in the standard model of cosmology to explain an accelerating expansion. And yet, there it was, staring back at them from the data. The explanation, if you can call it that, is dark energy. A mysterious form of energy that fills all of space, exerting a kind of negative pressure, pushing outward, accelerating the expansion. The name is a placeholder. Dark energy is not a thing we understand. It is a label for an effect we observe. We do not know what causes it. We do not know what it is made of. We do not even know if it is constant or if it changes over time. What we do know is that dark energy dominates the universe. It makes up about 68% of the total mass energy content, more than dark matter, more than ordinary matter, more than everything else combined. There are two leading models for what dark energy might be. The first is the cosmological constant, a term that shows up in Einstein's equations of general relativity. Einstein originally added the cosmological constant to his equations to make the universe static, to balance the pull of gravity and prevent the universe from collapsing. When Hubble discovered that the universe was expanding, Einstein called the cosmological constant his biggest blunder and removed it. But the term never went away. It just sat there in the equations, ignored for decades, and now it is back. If the cosmological constant is real, it represents the energy of empty space itself, a vacuum energy that has a constant density everywhere and at all times. Space has energy just by existing, and that energy pushes outward, driving the acceleration. The second model is called quintessence, a dynamic scalar field that changes over time. Unlike the cosmological constant, which is fixed, quintessence could vary in strength, increasing or decreasing as the universe evolves. Some versions of quintessence predict that dark energy will eventually dissipate, allowing gravity to take over and slow the expansion. Other versions predict that dark energy will keep growing stronger, accelerating the expansion faster and faster until space is ripped apart. We do not know which model, if either, is correct. Observations so far are consistent with a cosmological constant, but the data are not precise enough to rule out quintessence. The implications of dark energy are profound. If the acceleration continues, the universe will expand forever. Galaxies will move farther and farther apart. Eventually, in hundreds of billions of years, all the galaxies outside our local group will be so far away that their light will never reach us. The observable universe will shrink. Future civilizations, if they exist, will look up and see only the merged remnant of the Milky Way and Andromeda, surrounded by darkness. They will have no way to know that there were ever other galaxies. The evidence will have been stretched out of reach by the expansion of space. They will look at the sky and conclude that their galaxy is the entire universe. Everything we have learned about cosmology over the last century, the Big Bang, the expanding universe, the existence of billions of galaxies, all of it will be invisible to them. They will be living in a smaller, lonelier cosmos, and they will not even know what they have lost. Dark energy also determines the ultimate fate of the universe. If dark energy is constant, the universe will expand forever, cooling as it goes, until all the stars burn out, all the black holes evaporate, and nothing is left but cold, dark, empty space. That scenario is called the Big Freeze or the heat death. If dark energy grows stronger over time, the expansion could accelerate so violently that it tears galaxies apart, then stars, then planets, then atoms, ripping the fabric of space itself in an event called the Big Rip. If dark energy weakens, the expansion could eventually slow and reverse, pulling everything back together in a big crunch. We do not know which future awaits us. The answer depends on the nature of dark energy, and we do not understand dark energy well enough to predict what it will do. So here we are, living in a universe where 95% of the content is invisible. Dark matter holds galaxies together. Dark energy pushes them apart. Both are fundamental to the structure and evolution of the cosmos, and we have no idea what either of them is. It is humbling. We have sent probes to the edge of the solar system. We have mapped the cosmic microwave background. We have detected gravitational waves from colliding black holes. We have imaged the event horizon of a supermassive black hole. And yet, the two most dominant components of the universe remain complete mysteries. We can see their effects. We can measure their influence. We can build models that describe how they behave, but we cannot explain what they are or why they exist. This is not a minor gap in our knowledge. This is not a footnote waiting to be filled in. This is the foundation. Dark matter and dark energy are not exotic add-ons to an otherwise complete picture. They are the picture. The universe is made mostly of things we do not understand, and until we figure out what dark matter and dark energy actually are, everything else we know about cosmology rests on a foundation of ignorance. But there is one place where the darkness lifts, at least partially. One era where the universe was simpler, younger, more transparent. An era when there were no galaxies yet, no stars, no dark matter halos pulling things together, no dark energy accelerating the expansion. Just hydrogen and helium and light, cooling and expanding, setting the stage for everything that came after. That era is the early universe, and it is time to go back and see how all of this, the galaxies, the stars, the structure, the darkness, began. The universe was not always here. That sentence should feel obvious, but for most of human history it was not. The dominant assumption, from ancient philosophers through the Middle Ages and into the early 20th century, was that the universe was eternal. It had always existed in roughly the same form. It had no beginning. It would have no end. Stars might be born and die. Civilizations might rise and fall. But the cosmos itself was permanent, unchanging, infinite in time and space. That assumption felt natural because the alternative was uncomfortable. A universe with a beginning implied a moment of creation, and a moment of creation raised questions that science was not equipped to answer. So for a very long time, the universe was assumed to be timeless. It was easier that way. Albert Einstein believed it. When he finished developing the equations of general relativity in 1915 and 16, he applied them to the universe as a whole and discovered something disturbing. His equations predicted that the universe could not be static. It had to be either expanding or contracting. Gravity pulled everything together, so unless something was pushing outward to balance it, the universe should collapse. Einstein did not like that. He was so convinced the universe was static that he modified his own equations, adding a term called the cosmological constant to counteract gravity and keep the universe balanced. It was a patch, a fix, and Einstein knew it, but it worked. His modified equations allowed for a static universe, and the problem was solved, for a while. In 1927, a Belgian priest and physicist named Georges Lemaitre published a paper that changed everything. Lemaitre took Einstein's original equations without the cosmological constant and solved them properly. What he found was that the universe was not static, it was expanding. Lemaitre went further. If the universe was expanding now, then it must have been smaller in the past. Trace that expansion backward far enough, and you arrive at a moment when everything in the universe, all the matter, all the energy, all the space itself, was compressed into an infinitely small, infinitely dense point. Lemaitre called it the primeval atom. He proposed that the universe began as a single point that exploded outward, expanding and cooling, evolving into the cosmos we see today. It was the first mathematical description of what would later be called the Big Bang. Einstein hated it. He read Lemaitre's paper and told him, "Your math is correct, but your physics is abominable." The idea of a universe with a beginning felt too much like theology. It violated the principle of cosmic timelessness. It suggested a moment of creation, and Einstein, like most physicists of his time, was deeply uncomfortable with that implication. Lemaitre's work was dismissed. The universe remained static, at least in theory. Then, in 1929, Edwin Hubble published his observations of galaxy redshifts. He had measured the distances to dozens of galaxies and found that the farther away a galaxy was, the faster it was moving away from us. The relationship was linear, double the distance, double the speed. That was not what a static universe looked like. That was what an expanding universe looked like. Hubble's data confirmed what Lemaitre's equations had predicted. The universe was not standing still. It was flying apart. Every galaxy was moving away from every other galaxy, carried along by the expansion of space itself. Einstein saw the data and changed his mind. He called the cosmological constant his biggest blunder. He traveled to California to meet Hubble and see the observations firsthand. He publicly acknowledged that the universe was expanding and that Lemaitre had been right. The universe had a history. It was not eternal, it had a beginning. And that beginning, the moment when all the matter and energy in the cosmos was compressed into a single point, was the origin of everything. The term Big Bang was coined later, in 1949, by a British astronomer named Fred Hoyle during a radio broadcast. Hoyle was not a fan of the theory. He was championing an alternative model called steady-state cosmology, which proposed that the universe was eternal and unchanging on large scales, with new matter constantly being created to fill the voids left by expansion. Hoyle used the term Big Bang sarcastically, as a way to mock the idea of an explosive beginning. The name stuck, and ironically, Hoyle's steady-state model did not. By the 1960s, the Big Bang theory had become the leading explanation for the origin of the universe, but it still faced skepticism. The evidence was mostly indirect. Galaxy redshifts showed that the universe was expanding, but they did not prove it had started from a single point. There were other possible explanations. What the theory needed was a smoking gun, a piece of evidence so direct and so undeniable that it would close the debate. That evidence arrived in 1964, completely by accident, in the form of a faint hiss coming from every direction in the sky. Two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey, testing a large horn-shaped antenna designed to detect faint radio signals. They kept picking up an annoying background noise, a persistent static that showed up no matter where they pointed the antenna. They checked the equipment. They cleaned out pigeon droppings from the antenna, thinking the birds might be causing interference. The noise did not go away. It was always there, uniform, unchanging, coming from every direction with the same intensity. They could not explain it. Meanwhile, a group of physicists at Princeton University, led by Robert Dicke, had been working on a prediction. If the Big Bang theory was correct, the early universe would have been extremely hot, filled with high-energy radiation. As the universe expanded, that radiation would have cooled, stretched to longer wavelengths by the expansion of space. By now, billions of years later, that ancient radiation should have cooled to just a few degrees above absolute zero and should be detectable as faint microwave radiation coming from all directions. Dick and his team were planning to build an antenna to search for it. Then they heard about the noise Penzias and Wilson were picking up. Dick realized immediately what it was. "Somebody scooped us," he said. Penzias and Wilson had discovered the cosmic microwave background, the CMB, the leftover heat from the Big Bang. It was exactly what the theory predicted. A faint glow of radiation filling the entire universe, with a temperature of roughly 2.7 Kelvin, just a few degrees above absolute zero. The CMB is the oldest light in the universe. It is a snapshot of the cosmos as it existed 380,000 years after the Big Bang, the moment when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms and light could finally travel freely through space. Before that moment, the universe was opaque, a hot, dense fog where photons were constantly scattered by free electrons. After that moment, the universe became transparent. Light was free to travel, and it has been traveling ever since. The CMB is that light, stretched and cooled by billions of years of cosmic expansion, arriving at Earth today as a faint microwave signal. The discovery of the CMB was the turning point. It was direct observational evidence that the universe had been much hotter and denser in the past. It confirmed the Big Bang theory beyond any reasonable doubt. Penzias and Wilson won the Nobel Prize in Physics in 1978. The steady-state model collapsed, and cosmology, the study of the origin and evolution of the universe, became a precision science. The CMB is not perfectly smooth. Early observations suggested it was, but that created a problem. If the early universe was perfectly uniform, with no variations in density, then there would be no seeds for structure formation. Galaxies, galaxy clusters, the entire cosmic web, all of it requires regions of space that were slightly denser than average, overdensities that could collapse under gravity and grow into the structures we see today. If the CMB was perfectly smooth, those overdensities did not exist, and the universe should still be a uniform, featureless fog of gas. Obviously, it is not. In 1992, the COBE satellite, the Cosmic Background Explorer, detected tiny temperature fluctuations in the CMB, variations of about 1 part in 100,000. Those fluctuations are the fingerprints of the early universe, the tiny density differences that grew into galaxies and galaxy clusters over billions of years. Regions that were slightly warmer correspond to regions that were slightly denser. Regions that were slightly cooler correspond to regions that were slightly less dense. Those variations, imprinted into the fabric of space when the universe was less than 400,000 years old, are the seeds of everything that came after. The CMB is not just the oldest light in the universe, it is a map of the structure that would eventually become galaxies, stars, planets, and us. The Big Bang theory rests on 4 pillars of evidence. The first is Hubble's law, the observation that galaxies are moving away from us at speeds proportional to their distance, which shows that the universe is expanding. The second is the CMB, the leftover radiation from the early universe, which confirms that the universe was once much hotter and denser. The third is the abundance of light elements, hydrogen and helium. The Big Bang predicts that in the first few minutes after the universe began, nuclear fusion occurred, converting some of the hydrogen into helium and trace amounts of lithium. The predicted ratios match the observed ratios almost perfectly. About 75% hydrogen, 25% helium, with tiny traces of lithium. That is exactly what we see when we look at the oldest stars in the universe. The fourth pillar is the large-scale structure of the universe, the cosmic web, the filaments and voids, the clustering of galaxies. All of it matches the predictions of the Big Bang model. Those four pillars, galaxy redshifts, the CMB, light element abundances, and large-scale structure, are independent lines of evidence, and they all point to the same conclusion. The universe began in a hot, dense state approximately 13.7 to 13.8 billion years ago, and has been expanding and cooling ever since. There is still a problem. The Big Bang theory explains what happened from about 1 second after the beginning onward. It does not explain what happened before that. It does not explain what caused the Big Bang. It does not explain why the universe began in such a hot, dense state, and it does not explain why the universe is so uniform on large scales. The CMB has the same temperature in every direction to within 1 part in 100,000. That uniformity is a problem because different regions of the early universe, separated by vast distances, should not have been able to communicate with each other. The speed of light is finite. Information cannot travel faster than light. So how did opposite sides of the universe end up at the same temperature when they were never in contact? The answer, proposed in the 1980s by physicist Alan Guth, is cosmic inflation. Inflation is the idea that in the first fraction of a second after the Big Bang, the universe underwent a brief period of exponential expansion, doubling in size many times over in a span shorter than a blink. During that expansion, a tiny patch of space, smaller than an atom, inflated to the size of a galaxy or larger. That rapid expansion stretched out any irregularities, smoothing the universe and making it uniform on large scales. It also stretched quantum fluctuations, tiny random variations in energy density, to macroscopic scales. Those stretched fluctuations became the seeds of the density variations we see in the CMB, which later grew into galaxies. Inflation solves several problems at once. It explains why the universe is so uniform. It explains where the density fluctuations came from. And it predicts that the universe should be flat, meaning its large-scale geometry is Euclidean, not curved. Observations of the CMB confirm that the universe is flat to within a tiny margin of error. Inflation is not proven, but it is the best explanation we have for the initial conditions of the universe. And in March 2014, a team of scientists at the Harvard-Smithsonian Center for Astrophysics announced that they had detected variations in the CMB that supported cosmic inflation and provided evidence of gravitational waves from the first moments after the Big Bang. The announcement was later called into question, and the results have not been fully confirmed, but the search continues. If inflation is real, it is one of the most important ideas in cosmology. If it is not, then we have a lot of explaining to do. After inflation, after the universe expanded and cooled, there was a long dark period, the cosmic dark ages, not a poetic name, a literal description. From about 400,000 years after the Big Bang to roughly 50 to 100 million years later, the universe was dark. There were no stars, no galaxies, no light sources at all. Just neutral hydrogen and helium gas drifting through space, cooling as the universe expanded. The CMB was shining, but it was rapidly being redshifted into the infrared and beyond, no longer bright enough to illuminate anything. The universe was cold, dark, and quiet. Then gravity went to work. The tiny density fluctuations left over from inflation began to grow. Regions that were slightly denser attracted more matter. Dark matter, which does not interact with light or ordinary matter except through gravity, started collapsing first, forming the first dark matter halos. Ordinary matter, hydrogen and helium gas, fell into those halos, collected at the bottom, and began to compress. When the compression was strong enough, when the temperature and density at the core of a gas cloud reached the threshold, nuclear fusion ignited. The first stars were born. Those stars were different from any star we see today. They formed from pure hydrogen and helium, with no heavier elements, because heavier elements had not been created yet. Stars today form from gas clouds enriched by earlier generations of stars that lived, died, and scattered their guts into space. The first stars, called population 3 stars, had no such enrichment. They formed from the primordial gas left over from the Big Bang. And because that gas lacked the cooling mechanisms provided by heavier elements, the first stars had to form from much hotter and more massive clouds. The result was stars that were enormous, 30 to 300 times the mass of the Sun, millions of times brighter, burning hot and blue, radiating intense ultraviolet light. Those stars did not last long. A star that massive burns through its fuel in a few million years. When it dies, it does not fade quietly. It explodes as a supernova, one of the most violent events in the universe, blowing its outer layers into space and scattering the heavy elements forged in its core across the surrounding gas. Carbon, oxygen, nitrogen, iron, all the elements necessary for planets and life. The first stars seeded the universe with heavy elements, enriching the gas clouds from which the second generation of stars would form. That process repeated over and over. Each generation of stars added more heavy elements to the mix. Each generation built on the work of the one before. The Sun is a late arrival, a third or fourth generation star formed from a cloud of gas already enriched by billions of years of stellar evolution. The first stars did more than just create heavy elements. They ionized the surrounding gas. Their intense ultraviolet light stripped electrons from hydrogen atoms, turning neutral hydrogen into ionized hydrogen. That process, called reionization, lit up the universe. The cosmic dark ages ended. The universe became transparent again, not because it cooled, but because the first stars ionized the gas, clearing the fog. Reionization began roughly 50 to 100 million years after the Big Bang and took a few hundred million years to complete. By the time it was over, the universe was filled with light. The first stars, the first galaxies were shining. The dark ages were over. The first galaxies were not like the Milky Way. They were small, irregular, chaotic. A few million to a few billion stars packed into a region a few thousand light years across. No spiral arms, no organized structure, just clumps of stars held together by gravity, surrounded by dark matter halos. Those proto-galaxies merged with each other, colliding and combining, building larger structures over time. The process was messy, violent. Collisions triggered bursts of star formation. Gas was compressed and heated. Stars formed in dense clusters, lighting up the collision zones. Over hundreds of millions of years, those small proto-galaxies merged into the first large galaxies, the ancestors of the spirals and ellipticals we see today. The James Webb Space Telescope was built to see those first galaxies. Its infrared sensitivity allows it to peer through the dust and detect light from objects so distant that the light has been traveling toward us for over 13 billion years. Webb has found galaxies that existed when the universe was only a few 100 million years old, galaxies that are brighter and more massive than they should be according to the Standard Model. That discrepancy, which we talked about earlier, is forcing cosmologists to reconsider how quickly galaxies formed in the early universe. Either the models are wrong, or something is missing from our understanding of the first few 100 million years after the Big Bang. Webb is still collecting data. The answers are coming. The CMB is still here. It is everywhere. If you tune an old analog television to a channel with no signal, about 1% of the static you see on the screen is the CMB. That faint hiss is the echo of the Big Bang. Photons that have been traveling through space for 13.8 billion years, finally arriving at your living room, absorbed by your TV antenna, converted into random noise. You are seeing the oldest light in the universe, and it looks like static. That is humbling. The most important discovery in cosmology, the direct evidence that the universe had a beginning, shows up as noise on a broken television. The CMB has been mapped in exquisite detail by 3 major missions. COBE in the 1990s detected the first fluctuations. WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001, refined the measurements and gave us a detailed map of the temperature variations across the entire sky. Planck, a European Space Agency mission launched in 2009, pushed the precision even further, measuring the CMB to an accuracy of a few parts per million. The data from Planck has been used to calculate the age of the universe, 13.8 billion years, the composition of the universe, 5% ordinary matter, 27% dark matter, 68% dark energy, and the geometry of space, flat to within a tiny margin of error. All of that information is encoded in the tiny fluctuations in the CMB, the ripples in the ancient light. There is a tension in the data. The Hubble constant, the rate at which the universe is expanding right now, can be measured in 2 ways. One way is to use the CMB, the ancient light from the early universe, and run the equations forward to predict what the expansion rate should be today. That method gives a value of about 67 kilometers per second per megaparsec. The other way is to measure the distances to nearby galaxies and calculate the expansion rate directly. That method gives a value of about 73. The 2 numbers do not match, and they should. The discrepancy is called the Hubble tension, and it is one of the most important unsolved problems in cosmology. Either one of the measurements is wrong, or there is new physics happening that we do not understand. The tension has not been resolved. Observations keep confirming both numbers. Something is not adding up. The early universe was simpler than the universe today. Fewer elements, fewer structures, no planets, no life, just hydrogen, helium, dark matter, and light. But that simplicity is deceiving. Everything we see today, the galaxies, the stars, the planets, the complexity, all of it grew from the conditions set in the first few 100,000 years. The density fluctuations in the CMB, variations of 1 part in 100,000, were amplified by gravity over billions of years into the cosmic web, the filaments and voids, the clusters and superclusters. The first stars, formed from primordial gas, forged the heavy elements that make up planets and life. The first galaxies, small and irregular, merged into the spirals and ellipticals we see today. Every structure in the universe can be traced back to those first few 100 million years. The early universe set the rules. Everything since has been following them. The Big Bang is not a theory about an explosion. It is a theory about expansion. The universe did not explode into space. Space itself expanded, carrying matter along with it. There was no center, there was no edge. The Big Bang happened everywhere at once. Every point in space was once compressed into an infinitely small region, and every point in space has been expanding ever since. When we look at distant galaxies moving away from us, we are not seeing them flee from some central explosion. We are seeing space itself stretch, increasing the distance between galaxies, carrying them apart, and the expansion is accelerating. Dark energy is pushing space apart faster now than it was a billion years ago. The galaxies we see today will eventually move beyond the edge of the observable universe, stretched so far by the expansion that their light will never reach us. The universe is not just expanding, it is accelerating away from itself. The early universe, the hot, dense state from which everything emerged, is receding into the past, becoming more distant, more inaccessible, with every passing billion years. But the echo remains. The CMB is still here, the oldest light in the universe, a faint glow of microwave radiation filling the sky, carrying information from the first moments after the Big Bang, telling us where we came from and how we got here. It is the most important fossil in existence. Not a bone, not a rock. Light, ancient light, and it is everywhere. The early universe gave us the raw materials: hydrogen and helium, dark matter halos, density fluctuations. The first stars forged the heavy elements. The first galaxies assembled from proto-galactic clumps. Mergers built larger structures. Billions of years of cosmic evolution shaped the universe into what we see today. 200 billion galaxies, hundreds of billions of stars in each, planets, moons, and on at least one of those planets, life. Life that can look back at the CMB and understand what it is seeing. Life that can trace the history of the universe from the Big Bang to the present. Life that can ask where it came from and what happens next. The early universe gave us the raw materials: hydrogen and helium, dark matter halos, density fluctuations. The first stars forged the heavy elements. The first galaxies assembled from proto-galactic clumps. Mergers built larger structures. Billions of years of cosmic evolution shaped the universe into what we see today. 200 billion galaxies, hundreds of billions of stars in each, planets, moons, and on at least one of those planets, life. But that is the past. That is where we came from. The harder question, the one that keeps cosmologists staring at their models long into the night, is where we are going. What happens next? Not next year or next century, next trillion years, next 100 trillion years. What does the universe look like when it is old, when it is truly old? When every star has burned out and every galaxy has faded, and the expansion has stretched space so thin that nothing remains but cold, dark emptiness? The answer depends on which force wins: gravity or dark energy, attraction or repulsion, the pull that wants to bring everything together, or the push that wants to tear everything apart. Right now, they are both at work. Gravity holds galaxies together. Dark energy pushes galaxy clusters apart. And for the last few billion years, dark energy has been winning. The expansion of the universe is accelerating. Galaxies are moving away from each other faster now than they were in the past. And unless something changes, unless dark energy weakens or behaves differently than we expect, that acceleration will continue forever. There are three possible futures, three scenarios that depend on the nature of dark energy and how it evolves over cosmic timescales. The Big Freeze, the Big Crunch, the Big Rip. Those names are not official. They are labels invented by cosmologists to describe the end states of a universe governed by different assumptions about what dark energy actually is. And the uncomfortable truth is that we do not know which one is correct. We do not understand dark energy well enough to predict its behavior billions of years into the future. What we can do is map out the possibilities, trace each scenario to its logical conclusion, and see what the universe looks like in each case. None of the options are comforting, but one of them is almost certainly our future. Start with the Big Freeze, also called heat death. That is the most likely scenario based on current observations. It is the future we get if dark energy behaves like a cosmological constant, a fixed energy density that never changes. If that is true, then the universe will expand forever. The acceleration will continue. Space will stretch. Galaxies will move farther apart. And eventually, in hundreds of billions of years, every galaxy outside our local group will be so far away that its light will never reach us. The observable universe will shrink, the night sky will go dark, and then, slowly, over timescales so long that the current age of the universe becomes a rounding error, everything will shut down. The process is gradual. Stars do not all burn out at once. They age on different timescales depending on their mass. Massive stars, the blue giants and supergiants that dominate the night sky with their brightness, live fast and die young. A star 40 times the mass of the Sun burns through its fuel in only a few million years before exploding as a supernova. A star like the Sun, a mid-sized yellow dwarf, has a main sequence lifespan of about 10 billion years. The Sun is halfway through that now. In another 5 billion years, it will exhaust the hydrogen in its core, expand into a red giant, swallow the inner planets, and then shed its outer layers in a planetary nebula, leaving behind a white dwarf, a dense cooling ember roughly the size of Earth. That white dwarf will radiate heat for trillions of years, slowly fading as it cools, eventually becoming a black dwarf, a cold, dark remnant that no longer emits light. But the smallest stars, the red dwarfs, the M dwarfs, live far longer. These are stars with masses less than half the Sun, dim, faint objects that burn hydrogen so slowly they can remain on the main sequence for trillions of years, 10 trillion years, 20 trillion years. Some models push the lifespan of the smallest red dwarfs out to 100 trillion years or more. Those stars will outlive everything. They will still be shining long after the Sun has become a black dwarf, long after every massive star in the galaxy has exploded, long after the Milky Way and Andromeda have merged into Milkomeda and the merged galaxy has settled into a quiet old age with no gas left to form new stars. The red dwarfs will be the last lights in the universe, the final holdouts against the darkness. Star formation will end long before the last red dwarf burns out. By the time the universe reaches a cosmological decade of about 14, roughly 100 trillion years from now, essentially all normal star formation in galaxies will cease. That number is not arbitrary. It is based on models of how long galaxies can sustain star formation given their gas supplies and the rate at which gas is being consumed or ejected. Once the gas is gone, either converted into stars or blown out of the galaxy by supernovae and stellar winds, star formation stops. No more fuel. No more stars. The galaxy goes quiet. There is a strange coincidence in the numbers. The time scale for the end of star formation, about 100 trillion years, is roughly the same as the lifespan of the longest-lived red dwarfs. Star formation and stellar evolution end at roughly the same cosmic time. By the time the last red dwarf flickers out, the universe will have stopped making new stars billions of years earlier. The last generation of stars will die, and there will be no replacements. The era of stars, the period when the universe was filled with glowing fusion reactors, converting hydrogen into helium and lighting up the night sky, will be over. That era began about 50 to 100 million years after the Big Bang, when the first stars ignited. It will last for roughly 100 trillion years. After that, darkness. But the universe will not be empty. It will be full of remnants. White dwarfs, the cooling cores of dead sun-like stars. Neutron stars, the crushed remnants of massive stars that exploded as supernovae. Black holes, the collapsed cores of the most massive stars, objects so dense that not even light can escape their gravity. And brown dwarfs, failed stars that never got hot enough to sustain hydrogen fusion, halfway between a planet and a star, dim and cold from the start. Those objects do not emit light, or at least not enough to matter. A white dwarf glows faintly from residual heat, but that heat fades over trillions of years. A neutron star spins and emits radiation, but eventually it slows down and goes quiet. A black hole does not emit anything except Hawking radiation, a theoretical form of radiation so faint it has never been detected. The universe will be full of these objects, trillions upon trillions of dark remnants scattered across space, invisible, inert, slowly cooling toward absolute zero. Galaxies will fade. The Milky Way, or rather Milkomeda, the merged remnant of the Milky Way and Andromeda, will still exist as a structure. Gravity will still hold it together. The stars, or what used to be stars, will still orbit the galactic center. But there will be no light, no glow, no spiral arms lit up by young hot stars. Just a dark cloud of white dwarfs and neutron stars and black holes drifting through space, bound together by gravity, invisible against the void. Other galaxies will look the same, dark, cold, dead. And they will be moving away from each other, carried by the expansion of space, accelerating into the distance until they are so far apart that they can no longer interact. The universe will become a collection of isolated dark galaxies, each one alone in an ever-expanding emptiness, with no way to communicate, no way to reach each other, separated by distances so vast that even light, traveling for trillions of years, would never close the gap. That is the Big Freeze. A universe that expands forever, cools to near absolute zero, and ends not with a bang, but with a whimper. No explosions, no catastrophic collapse, just a slow fade. The stars burn out, the galaxies go dark, the black holes evaporate. And eventually, after timescales so incomprehensibly long that the current age of the universe, 13.8 billion years, becomes an eye blink, the universe reaches a state of maximum entropy, a condition where no energy is available to do work, no structures can form, and nothing ever changes again. Heat death, the Big Freeze, the most probable end of everything. There is a variation, the Big Crunch. That is what happens if dark energy weakens or disappears. If the expansion of the universe slows down, if the acceleration reverses, if gravity eventually wins, then the universe could stop expanding and start contracting. Space would begin to shrink. Galaxies would stop moving apart. They would slow down, turn around, and start falling back toward each other. Over billions of years, the contraction would accelerate. Galaxies would collide and merge at increasing rates. The cosmic microwave background, currently cooled to 2.7 Kelvin, would start to heat up as space contracted and the wavelengths of light were compressed. The universe would grow warmer, hotter. The night sky would glow, first faintly, then brightly, as the CMB was blue shifted back into visible light. Eventually, the contraction would reach a point where galaxies were ripped apart by tidal forces. Stars would be torn from their orbits, planets would be vaporized, matter would compress into a hot, dense state, similar to the conditions in the early universe but in reverse. The Big Crunch would end with everything collapsing back into a singularity, a point of infinite density, the opposite of the Big Bang. And then, maybe it would all start over, a new Big Bang, a new universe, a cycle repeating forever. That scenario is not ruled out by the data, but it requires dark energy to behave in a way we have not observed. Current measurements suggest that dark energy is constant, or at least very close to constant. It is not weakening, it is not fading, and if it stays constant, the universe will not collapse. The expansion will continue. The Big Crunch is possible in principle, but it does not look likely. The universe is not slowing down, it is speeding up. Then there is the Big Rip. That is the nightmare scenario, the one that happens if dark energy gets stronger over time. If the acceleration of the expansion increases, if the push outward grows more violent, then dark energy could eventually overpower not just the expansion of space, but the forces holding structures together. Gravity holds galaxies together. Electromagnetic forces hold atoms together. If dark energy keeps growing, it could tear galaxies apart, then star systems, then planets, then molecules, then atoms, then subatomic particles. The universe would be ripped apart at every scale, shredded by an accelerating expansion that does not stop until nothing is left but isolated quarks and photons scattered across an infinite void. The timeline depends on how fast dark energy strengthens. Some models put the Big Rip about 20 billion years in the future. Others push it out to hundreds of billions of years. The mechanism is the same. Dark energy, instead of remaining constant, increases in strength as the universe expands. At first, the effects are subtle. The expansion accelerates a bit faster than expected. Galaxy clusters stop forming. The cosmic web begins to dissolve. Then the acceleration picks up. Galaxies are torn apart, their stars flung into intergalactic space. Stellar systems are disrupted. Planets are ripped from their orbits. As the acceleration continues, the forces holding matter together start to lose. Chemical bonds break, molecules disintegrate, atoms are torn apart, their electrons stripped away. Finally, even atomic nuclei are shredded, protons and neutrons ripped into their constituent quarks. The universe ends not in cold darkness, but in violent disintegration, torn apart by its own expansion, leaving nothing but a scattering of fundamental particles that can never interact again. The Big Rip is not the leading scenario. Current observations suggest that dark energy is constant, or very nearly so. A cosmological constant does not grow stronger over time. It just sits there, pushing space apart at a steady rate, driving the expansion without increasing in strength. But we do not know for sure. Dark energy is the least understood component of the universe. We do not know what it is, we do not know what causes it, and we do not know how it will behave over timescales of billions or trillions of years. If dark energy is not a cosmological constant, if it is something dynamic, something that changes, then the Big Rip is back on the table. And that is terrifying. There is another possibility: vacuum decay. The idea is that the universe exists in a metastable state, a false vacuum, and that at any moment a quantum fluctuation could trigger a collapse into a lower energy state, a true vacuum. If that happens, a bubble of true vacuum would form and expand at the speed of light, rewriting the laws of physics inside it, destroying everything in its path. Stars, galaxies, atoms, all of it would cease to exist, replaced by a new configuration of matter and energy governed by different physical constants. The bubble would expand forever, consuming the entire universe, and there would be no warning. No way to see it coming, no way to escape. One moment the universe exists, the next moment it does not. Vacuum decay is speculative. There is no evidence it will happen, but there is also no evidence it will not. The universe could end tomorrow, or in a billion years, or never. We have no way to know. Most cosmologists bet on the Big Freeze, a universe that expands forever, cools down, and fades into darkness. That is the scenario supported by the data. That is the future implied by a cosmological constant and an accelerating expansion. And if that is correct, then the universe has a finite window of activity. Right now, 13.8 billion years after the Big Bang, the universe is in its prime. Stars are forming, galaxies are colliding and merging, planets are forming around young stars. Life exists, at least on Earth, and possibly elsewhere, but that window will close. In 100 trillion years, star formation will end. In a few 100 trillion years, the last red dwarf will burn out. In a quadrillion years, the white dwarfs will have cooled to black dwarfs. In 10 to the 100 years, black holes will have evaporated through Hawking radiation, leaving behind nothing but photons and low-mass particles. The universe will be dark, cold, empty, and it will remain that way forever. This is not a distant, abstract problem. This is the future, the actual future, the place where every trajectory ends, and it is worth sitting with that for a moment. The universe, as far as we can tell, is not eternal. It had a beginning, it will have an end, not in the sense that it will cease to exist, but in the sense that it will reach a final state from which nothing new can emerge. No more stars, no more galaxies, no more complexity. Just an infinite expanse of cold, empty space, littered with the dark remnants of everything that once was, drifting alone, unable to interact, slowly cooling toward absolute zero. That future is incomprehensibly distant, trillions of years away, quadrillions, numbers so large they lose meaning. The universe has existed for less than 14 billion years. The timescale for the Big Freeze is 10 trillion years or more. We are closer to the Big Bang than we are to the end. The universe is young. It is in the early chapters of its story, but the ending is written, at least in broad strokes. Unless dark energy behaves differently than we think, unless new physics intervenes, unless something we have not accounted for changes the rules, the universe is headed toward heat death, a slow fade into darkness. But here is the thing. That future, distant as it is, only matters if there is someone around to witness it. And that brings us back to now, to this moment, to this brief flicker of light between the Big Bang and the Big Freeze. We exist in a universe that is still young, still active, still capable of producing stars and planets and, possibly, life. We live in the era when the universe is brightest, when the stars are still shining, when galaxies are still colliding, when complexity is still increasing. That era will not last. It cannot last. The laws of thermodynamics are clear. Entropy increases, order decays, complexity gives way to simplicity, and eventually the universe will settle into a state where nothing interesting can happen ever again. But we are not there yet. We are here, now. In the only window of cosmic history where a species like ours could exist, could look up at the night sky, could ask where we came from and where we are going. The universe gave us a narrow opening, a brief period, cosmically speaking, when conditions were right for life. Stable stars, rocky planets, liquid water, complex chemistry. That opening will close. The stars will burn out. The planets will freeze. And whatever came after us, if anything does, will inherit a darker, colder universe, one step closer to the final fade. The distant future is not kind. It is not hopeful. It offers no redemption, no second chances, no miraculous reversals. The universe is running down. Slowly, yes, but inevitably. And when it is done, when the last star has burned out and the last black hole has evaporated, there will be nothing left but the memory of what once was, encoded in the positions and velocities of particles that no longer interact, scattered across a space too vast for anything to ever find anything else again. That is the distant future. That is where this is all going. But it is not where we are, not yet. We are still here, on a pale blue dot orbiting a mid-sized star in the suburbs of an average galaxy, living in the brief bright window between the Big Bang and the Big Freeze. And that might be the most important fact of all. The universe is not infinite in time, it is finite, bounded. And we are living in the part that matters, the part where things can still happen, where stars still shine, where life still exists, where the question of what it all means still has time to be asked. The distant future is dark, but the present right now is not. And that makes all the difference. The distant future is dark, but the present right now is not. And that makes all the difference. Because here is the thing about the universe that nobody talks about. It does not care. It is not hostile. It is not cruel. It is just indifferent. The universe does not notice you. It does not notice Earth. It does not notice the Milky Way. It operates according to physical laws that were set in motion 13.8 billion years ago and have been running without interruption ever since. Gravity pulls, space expands, stars burn, black holes evaporate, entropy increases. The laws do not bend. They do not make exceptions. They do not pause for applause, and they certainly do not care whether anyone is watching. But we are watching. And that might be the strangest thing in the entire cosmos. Somewhere in the middle of 200 billion galaxies, on a planet orbiting an average star in an unremarkable spiral galaxy, matter has organized itself into a pattern complex enough to look back at the universe and understand what it is seeing. Atoms forged in the cores of dying stars have arranged themselves into brains capable of contemplating their own origin. Carbon and oxygen and nitrogen, elements that did not exist in the early universe, elements that had to be built inside stellar furnaces and scattered across space in supernova explosions, have somehow assembled into structures that can do calculus, write poetry, and ask why. That is not normal. That is not expected. That is, as far as we know, extraordinarily rare. We do not know how rare. That is the uncomfortable part. We have been searching for other life, other intelligences, for decades. We have pointed radio telescopes at the sky and listened for signals. We have sent messages into space, golden records attached to Voyager probes, carrying greetings in 55 languages and recordings of Earth sounds, just in case someone out there finds them and wants to know who we are. We have studied thousands of exoplanets, looking for signs of atmospheres that could support life, chemical signatures that might indicate biology, and so far we have found nothing. Not a single microbe, not a radio signal, not a trace of technology, not even a hint of organic chemistry on another world that could not be explained by geology. We are, as far as the data shows, alone. That could mean two things. Either life is so rare that it has only happened once in this corner of the universe, or life is common, but intelligence is the bottleneck. Maybe the universe is filled with bacteria. Maybe every planet with liquid water and a stable energy source develops microbial life within a few 100 million years. But maybe the jump from single-celled organisms to complex multicellular life is rare. Maybe the jump from multicellular life to intelligence is even rarer. Maybe we are the only species in the Milky Way that has ever looked up at the night sky and wondered what those lights are. That would make us unimaginably precious. It would also make us unimaginably lonely. Or maybe we are just early. The universe is young. It has existed for less than 14 billion years. The smallest stars, the red dwarfs, will burn for trillions of years. If life takes time to develop, if intelligence takes even longer, then maybe we are the first generation. Maybe in 1 trillion years, the galaxy will be filled with civilizations, and they will look back at this era the way we look back at the cosmic dark ages, a time before anything interesting had happened. We could be pioneers, the first minds in a universe that will eventually be crowded with them. Or we could be alone, permanently, the only species that ever got this far, the only ones who ever looked up and asked why. We do not know, and until we find someone else, or prove definitively that there is no one else, we will not know. But either way, the fact that we are here, right now, at this moment in cosmic history, is not an accident. It is a coincidence, yes, but it is a meaningful one. Because the window for observation, the era when the universe is transparent enough and stable enough and filled with enough light to allow complex life to evolve and study the cosmos, is narrow, narrower than most people realize. We exist in a Goldilocks moment, not too early, not too late, just right. Too early, and the universe would have been too chaotic. The first few 100 million years after the Big Bang were violent. The first stars were massive and short-lived, exploding as supernovae and flooding space with radiation. There were no heavy elements yet, no carbon or oxygen or nitrogen, nothing to build planets or life. The first galaxies were small and colliding constantly, their gas clouds compressed and ionized by the radiation from young stars. It was a rough neighborhood. Life, if it could have formed at all, would have been sterilized by the next nearby supernova within a few million years. The universe needed time to settle down, to build up a reservoir of heavy elements, to form stable stars and planets in regions far enough from the galactic center to avoid constant bombardment. That took billions of years. The Sun formed 4.5 billion years ago. The universe was already more than 9 billion years old by then. We are not first generation. We are late arrivals. Too late, and the universe will be too dark. In a few 100 billion years, star formation will end. The gas supply will run out. Galaxies will fade as their stars age and die. The cosmic microwave background, already cooled to 2.7 Kelvin, will stretch to even longer wavelengths, becoming undetectable. The expansion of space will carry distant galaxies beyond the observable horizon. Future civilizations, if they exist, will look up and see only their own galaxy, surrounded by darkness. They will have no way to know that other galaxies ever existed. They will have no evidence of the Big Bang. They will have no cosmic microwave background to study. The entire history of cosmology, everything we have learned about the universe over the last century, will be inaccessible to them. They will be living in a smaller, lonelier cosmos, and they will not even know what they have missed. The universe is giving us a gift right now, a view, a perspective, a chance to see the full scale of creation before the lights go out. And that gift has an expiration date. We are living in the only era when the cosmic microwave background is detectable, when distant galaxies are still visible, when the expansion of the universe is slow enough that we can measure it, but fast enough that we can prove it is happening. We are living in the only era when the night sky is filled with stars from other galaxies, when the evidence of the Big Bang is written in the light reaching us from the edge of the observable universe. A few 100 billion years from now, that evidence will be gone. The universe will have expanded so much that the light from distant galaxies will never reach whoever is still around to look. The cosmic microwave background will have redshifted into oblivion. The entire story of the universe, from the Big Bang to the formation of galaxies to the era of stars, will be invisible. Future astronomers will have to take it on faith that the universe was ever any different than what they see. And if they are anything like us, they will not take things on faith. They will demand evidence. And the evidence will not be there. We have the evidence, right now, today. We can see the cosmic microwave background. We can measure the redshifts of distant galaxies and calculate the expansion rate. We can map the large-scale structure of the universe, the cosmic web, the filaments and voids. We can trace the history of the cosmos from the first fraction of a second after the Big Bang to the present day. We are living in the golden age of cosmology, the brief window when the universe is old enough to have interesting structure, but young enough to still show us how it got here. And we almost missed it. If humans had evolved a few 100 million years earlier, we would not have had the technology to detect the cosmic microwave background or measure galaxy redshifts. If we had evolved a few 100 billion years later, there would have been nothing to detect. We are here at exactly the right time, not by design, by luck, by a cosmic coincidence that placed us in the one era when the universe is knowable. That is the Goldilocks condition. Not just liquid water on a rocky planet in the habitable zone of a stable star. That is the biological Goldilocks condition. The cosmological Goldilocks condition is existing in the one era when the universe reveals its history, when the evidence is still visible, when the night sky is not yet dark, when the galaxies have not yet receded beyond reach. We are living in the sweet spot, and the clock is ticking. There is another Goldilocks condition, the one Carl Sagan talked about. The one that says, we are the universe becoming aware of itself. That phrase gets thrown around a lot, usually in inspirational posters or philosophy classes. But it is not just poetic nonsense, it is literally true. The atoms in your body were forged in stars. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was created inside stellar cores through nuclear fusion and scattered into space when those stars exploded. You are made of stardust. That is not a metaphor, that is chemistry. Every element heavier than hydrogen and helium in your body was built inside a star that died billions of years ago. And the debris from that star eventually drifted into a molecular cloud, collapsed under gravity, and formed the sun and the planets and you. You are not separate from the universe. You are a piece of it. A very small piece, yes, but a piece that can think, and that thinking matters. Because for the first 13 billion years of cosmic history, the universe just existed. It expanded, it cooled, it formed stars and galaxies and planets. It followed the laws of physics without deviation, without awareness, without anyone watching. It was a process. A very long, very complicated process, but just a process. Then, about 4 billion years ago, on one planet orbiting one star in one galaxy, chemistry became biology. Molecules started replicating. Evolution began. Over billions of years, that biology became more complex. Single cells became multicellular organisms. Multicellular organisms developed nervous systems. Nervous systems developed brains. Brains developed consciousness. And consciousness developed curiosity. Somewhere along that chain, matter stopped just existing and started asking questions. Why am I here? Where did I come from? What is this place? Those questions are not trivial. They are the first time in the history of the universe that the universe has ever been able to ask anything about itself. We are not observers standing outside the cosmos looking in. We are the cosmos looking at itself. We are the universe's way of knowing that it exists. That is extraordinary. That is maybe the most extraordinary thing that has ever happened. For 13 billion years, the universe was unconscious. It operated according to physical laws, but it had no idea those laws existed. Stars burned, galaxies collided, planets formed, and none of it meant anything because there was no one around to notice. Then we showed up, and suddenly, for the first time, the universe had a mirror, a way to see itself, a way to understand itself. We are that mirror. We are the universe's self-awareness. And the fact that we exist at all, that matter can organize itself into patterns complex enough to contemplate the cosmos, is so statistically improbable that it borders on miraculous. Except it is not a miracle, it is physics, very complicated physics. But physics nonetheless. The conditions required for that complexity are narrow. Earth sits in the habitable zone of the Sun, the narrow band of distances where liquid water can exist on the surface of a rocky planet. That zone is roughly 120 million kilometers wide. Too close to the Sun, and water boils away. Too far, and it freezes. Earth is right in the middle, at about 1 astronomical unit, roughly 150 million kilometers from the Sun. Venus, at 0.7 astronomical units, is too close. Mars, at 1.5 astronomical units, is too far. The difference between a habitable planet and a dead one is less than the distance from Earth to Mars. That is how narrow the window is. But the habitable zone is not enough. You also need a stable star. The Sun is a G-type main sequence star, burning hydrogen steadily for billions of years without dramatic flares or variations in brightness. Many stars are not stable. Red dwarfs, the most common type of star in the galaxy, are prone to violent flares that would strip away a planet's atmosphere. Massive stars burn too hot and too fast, living only a few million years before exploding. The Sun is just right. Stable, long-lived, and sitting in a quiet part of the galaxy where the radiation environment is low and the risk of catastrophic events like nearby supernovae is minimal. We are not near the galactic center, where the density of stars is high and the radiation from the supermassive black hole would sterilize anything nearby. We are not in a star-forming region, where supernovae are common and the radiation levels are lethal. We are in the suburbs, the safe zone, the boring part of the galaxy where nothing dramatic happens and life has time to evolve without being wiped out every few million years. You also need a large moon. Earth's moon, unusually large for a planet of Earth's size, stabilizes the planet's axial tilt, preventing wild swings in climate that would make long-term habitability difficult. You need plate tectonics, which recycle carbon and regulate the climate over geological timescales. You need a magnetic field, generated by a molten iron core, which shields the surface from the solar wind and prevents the atmosphere from being stripped away. You need a gas giant like Jupiter in the outer solar system, acting as a gravitational shield that deflects comets and asteroids that would otherwise bombard the inner planets. Every one of those factors is necessary. Remove any one of them, and Earth becomes uninhabitable. The fact that they all lined up, that every condition happened to be met, is not evidence of design. It is evidence of how rare habitability is. Out of thousands of exoplanets discovered so far, only a handful sit in the habitable zone of their stars. And of those, we do not know if any have moons or magnetic fields or plate tectonics or gas giants protecting them. We do not know if any of them are actually habitable. We just know that Earth is, and that makes Earth, at least for now, unique. But the Goldilocks conditions are not permanent. They have a shelf life. The Sun is getting brighter. It has been getting brighter since it formed 4.5 billion years ago, and it will continue to get brighter as it ages. In about 1 billion years, the Sun will be 10% brighter than it is today. That might not sound like much, but it is enough to push Earth out of the habitable zone. The oceans will evaporate. The atmosphere will thicken with water vapor, trapping heat, creating a runaway greenhouse effect similar to what happened on Venus. Earth will become uninhabitable, not because of anything humans did, but because the Sun got older. The window for life on Earth is not infinite, it is finite. And the closing date is already set, 1 billion years. That is how much time we have left, assuming nothing else wipes us out first. 1 billion years sounds like a long time. It is a long time, but compared to the age of the universe, it is nothing. The universe is 13.8 billion years old. Earth has been habitable for about 4 billion years. It will remain habitable for roughly 1 more billion. That is a total window of 5 billion years out of a cosmic timeline that stretches for trillions. We are living in the middle of that window, the Goldilocks era. The brief period when conditions are right for complex life, when the universe is transparent and knowable, when the stars are still shining and the galaxies are still visible, and the evidence of cosmic history has not yet been erased by expansion. We are here now, at the exact moment when the universe can be understood. And that is not an accident. It is a coincidence, a very, very lucky coincidence. So what do we do with that? What is our responsibility, if we even have one? The universe does not ask anything of us. It does not require us to understand it. It will keep expanding and cooling and fading, whether we pay attention or not. But we are here. We have the capacity to understand. We have built telescopes and satellites and detectors that can see across billions of light years and map the structure of the cosmos. We have decoded the cosmic microwave background and traced the history of the universe back to the first fraction of a second. We have figured out where we came from, how we got here, and where we are going. That knowledge does not come with a manual. It does not tell us what to do, or how to live, or whether any of this matters. It just is. A set of facts about the universe, a map of the terrain, and what we do with that map is up to us. But here is the thing. The map will not be available forever. The evidence is fading. The distant galaxies are receding. The cosmic microwave background is cooling and redshifting into invisibility. In a few 100 billion years, everything we have learnt will be gone, erased by the expansion of space. If there is anyone around to inherit the universe after us, they will not have the tools we have. They will not be able to see what we see. They will be living in a darker, smaller cosmos, and they will have to take our word for it that the universe was ever any different. That puts us in a unique position. We are the witnesses, the ones who saw the universe in its youth, when it was still bright, when the evidence was still visible, when the story could still be told. And if we do not tell that story, if we do not preserve what we have learned, it will be lost, not forgotten, lost irretrievably, because the universe will have moved on and the evidence will no longer exist. That might be our role, not to control the universe or bend it to our will or escape the inevitable heat-death trillions of years from now. We cannot do any of those things. The universe is too large, too old, too indifferent to care what we want. But we can be the record keepers, the archivists, the ones who looked up, figured out what we were seeing, and wrote it down. We can be the species that understood. That might be enough. It might have to be. There is a deeper question, one that does not have a scientific answer. Why does any of this exist at all? Why is there something instead of nothing? The Big Bang explains how the universe evolved from a hot, dense state into the cosmos we see today. It does not explain why there was a hot, dense state in the first place. It does not explain where the laws of physics came from or why they are what they are. It does not explain why the universe is structured in a way that allows for stars and planets and chemistry and biology and consciousness. Those are not questions science can answer. They are questions that sit at the boundary between physics and philosophy, and they have been asked for as long as humans have been capable of asking questions. And we still do not have answers, but we keep looking. That is the other part of being human. We do not stop asking just because the answers are hard or because the universe does not hand them to us. We build better telescopes. We run deeper simulations. We send probes to the outer solar system and beyond. We search for exoplanets and study their atmospheres. We map the cosmic web and measure the expansion rate and hunt for dark matter particles and try to figure out what dark energy actually is. We keep pushing at the edges of what we know, not because we expect to find some final ultimate truth that explains everything, but because the process of looking, the act of trying to understand, is what makes us human. Curiosity is not optional. It is who we are. It is the thing that separates us from every other species on this planet. We are the ones who look up and ask why. And as long as we are here, we will keep asking. The universe is vast. It contains 200 billion galaxies. Each galaxy contains hundreds of billions of stars. Each star could have planets. The numbers are so large they stop meaning anything. But somewhere in that vastness, on one small rocky planet orbiting one average star in one unremarkable galaxy, matter has organized itself into a pattern that can look back at the cosmos and understand what it is seeing. That pattern is temporary. It will not last. In 1 billion years, Earth will be uninhabitable. In 100 trillion years, the stars will burn out. In 10 to the 100 years, the black holes will evaporate and the universe will reach heat death. Everything that has ever existed, every thought, every idea, every piece of knowledge will be gone. The universe will continue, but it will be dark and empty, and nothing will ever happen again. But that is the future, a future so distant it might as well be infinite. We are not there yet. We are here, now. In the brief, bright window between the Big Bang and the Big Freeze. In the Goldilocks era, when the universe is knowable, when the stars are still shining, when the evidence of cosmic history is still visible. We exist in the one moment when complex life is possible, when intelligence can evolve, when consciousness can look up and understand. That moment will pass, but it has not passed yet. And as long as we are here, as long as we have the capacity to ask questions and search for answers, we have a responsibility to keep looking. Not because the universe requires it, because we do. Because the act of understanding, the process of figuring out where we came from and what this place is the most human thing we can do. It is what makes us more than just another species. It is what makes us witnesses. The universe's way of knowing itself, and that, in a cosmos that is mostly empty and mostly dark and mostly indifferent, might be the closest thing to meaning we are ever going to find. We are here, now, on a pale blue dot orbiting an average star in an ordinary galaxy, in a universe filled with 200 billion other galaxies just like it. We are made of atoms forged in the cores of dying stars. We are a pattern of matter complex enough to contemplate its own existence. We are the universe looking back at itself and asking why, and for a brief moment, cosmically speaking, we have the tools to answer that question. The telescopes, the data, the evidence, the map, the window is open. The view is clear, and the clock is ticking. What we do with that window, with that view, with that fleeting moment of clarity is up to us. But the fact that we are here at all, that we exist in the one era when the universe can be understood, is not an accident. It is a gift, a cosmic coincidence, a Goldilocks moment. And it will not last forever. So we keep looking, we keep asking, we keep searching. Because that is what we do, that is who we are. We are the ones who looked up, and we are still looking. We started with a photograph, a pale blue dot suspended in a beam of scattered sunlight, captured by a machine 6 billion kilometers from home. That image was supposed to humble us. It did. But somewhere along the way, as we traced the path from that dot outward, through the Milky Way and the local group and the cosmic web and the 200 billion galaxies scattered across space and time, something else happened. The humbling turned into something stranger, not pride exactly, not arrogance, but a quiet, uncomfortable realization that the universe gave us a gift we did not ask for and do not entirely deserve. We exist in the only era when the cosmos can be understood. A few 100 million years earlier, and we would not have had the technology to see it. A few 100 billion years later, and there would be nothing left to see. The distant galaxies will have receded beyond the horizon. The cosmic microwave background will have faded into noise. The evidence of the Big Bang, the expansion, the entire history we have spent a century piecing together will be gone. Erased not by time, but by space itself, stretched beyond retrieval by the accelerating expansion. Future civilizations, if they exist, will inherit a darker, smaller universe. They will look up and see only their own galaxy surrounded by emptiness, and they will have no way to know it was ever any different. But we know. We are here now, in the narrow window, when the universe is transparent, when the stars are still burning, when the night sky is filled with light from objects billions of years old. We are living in the brief moment when matter can look back at itself and understand what it is seeing. That moment is not permanent. It is not guaranteed. It is a cosmic accident, a Goldilocks era that opened without warning and will close without asking permission. The window is open. The view is clear and the clock is ticking.